Before we can understand how stars die, we need to understand what they are. And the answer is both simple and profound. A star is a ball of gas held together by its own gravity, so massive and so compressed that its core becomes hot enough to fuse atoms together. That is it. That is a star. Gas and gravity and fusion. But from these three simple ingredients comes everything: light, heat, the elements that make planets, the energy that powers life. Our sun is a star. Not a special one, not particularly large or small or bright, just average. One of perhaps 200 billion stars in our galaxy. And our galaxy is one of perhaps 200 billion galaxies in the observable universe. Stars are everywhere, and they are all doing essentially the same thing, fighting against gravity by burning fuel. Imagine a star as a tug of war. Gravity pulls inward, trying to collapse the star into a single point. But fusion in the core releases energy, heat and light and pressure. That pushes outward. As long as these forces balance, the star is stable. It shines, it lives. Our sun has been in this balance for about 4.6 billion years. Every second, it fuses about 600 million tons of hydrogen into helium. That is happening right now, in the core, 93 million miles away from you. The sun is burning, has been burning since before Earth existed, will keep burning for billions of years more. But, and this is important, the sun is using fuel. Hydrogen is finite. There is a lot of it, enough to last billions of years, but it is not infinite. Every second the sun shines. It is consuming hydrogen that can never be replaced, which means every star has a lifetime. A beginning, a middle, and an end. The moment a star begins fusing hydrogen, it starts the countdown to when that hydrogen will run out. And what happens then? What happens when the fuel is gone? What happens when gravity finally wins the tug of war? That is what we are here to explore, not with anxiety or dread, but with curiosity and calm. Because the death of stars is not a tragedy. It is a transformation. It is necessary. It is beautiful. Stars die so that new stars can be born. They die so that planets can form. They die so that carbon and oxygen and iron, the atoms that make up your body, can be scattered into space, ready to become something new. Death in the cosmos is not an ending. It is a transition, a change of state, a return to the universe, so that the universe can continue creating. And as you rest here, breathing slowly, letting your body relax, you can think about this. You are made of dead stars. The atoms in your bones, your blood, your brain, they were forged in the cores of stars that died billions of years ago. You are stardust. And someday, in the very distant future, the atoms that make you will return to space, scattered and recycled. And tonight, we'll learn how they do it. Most stars spend most of their lives doing exactly what our sun is doing right now, sitting on what astronomers call the main sequence, calmly fusing hydrogen into helium, shining steadily, changing so slowly that the change is invisible across human lifetimes. The main sequence is the long, stable middle age of a star's life. It is not dramatic, nothing explodes, nothing collapses. The star just shines. Day after day, year after year, millennium after millennium, burning its fuel at a rate determined by its mass. How long does this last? It depends on the star's size. Massive stars, those 10, 20, 50 times the mass of the sun, burn hot and bright. They reprofligate with their fuel, consuming it rapidly. A star 50 times the sun's mass might stay on the main sequence for only a few million years. That sounds like a long time, but in cosmic terms, it is a blink. These stars live fast and die young. Medium stars like our sun are more conservative. They burn their hydrogen slowly, carefully, making it last. The sun will spend about 10 billion years on the main sequence. It is halfway through that now, about 4.6 billion years old, with another 5 billion years of stable, burning ahead of it. And small stars, red dwarfs, the most common type of star in the universe, are misers with their fuel. They burn so slowly, so coolly, that they can stay on the main sequence for tens of billions of years, some for 100 billion years or more. The universe is only 13.8 billion years old, which means every red dwarf ever born is still on the main sequence. None has had time to die yet. Think about that. Stars so long lived that none has ever reached old age. They'll shine for longer than the universe has existed so far, patient and dim and eternal by any standard we can imagine. But even they will die eventually. Even the smallest, slowest burning stars will someday exhaust their hydrogen. The fuel will run out, the core will cool, and the balance between gravity and pressure will shift. For now, though for billions of years most stars just shine, they sit in space converting mass into energy according to Einstein's equation, e.m.c. Every second, a tiny fraction of their mass becomes light and heat, radiating outward, traveling across the galaxy, sometimes reaching planets where that light becomes warmth, becomes photosynthesis, becomes life. Our sun is doing this right now. Its light left the surface 8 minutes ago and is just now reaching Earth, falling on oceans and forests and your closed eyelids. The sun doesn't know you are here, doesn't care. It just shines, as it has been shining for billions of years, as it will shine for billions more. The main sequence is the calm before the change, the long stable period when a star is most itself, burning steadily, unchanging, predictable. It is the majority of a star's life, and it is peaceful, no drama, no crisis, just the quiet work of fusion, turning hydrogen into helium, photon by photon, second by second, year after year. But eventually, that work will end, the hydrogen will run out, and the star will have to change. Nothing lasts forever. Not mountains, not oceans, not stars. Everything that begins must eventually end, and stars are no exception. But why? Why can't a star just burn forever? The answer is simple. Fuel is finite. A star is born with a certain amount of hydrogen. A lot, yes, but not infinite. And every second it shines, it is using some of that hydrogen up, fusing it into helium, converting it from fuel into ash. In the beginning, the star's core is pure hydrogen, perfect fuel, burning efficiently, producing energy steadily. But as the star ages, helium accumulates in the core. Helium is the ash of hydrogen fusion, and it just sits there, inert, not burning, not contributing energy. Think of it like a fireplace. As you burn wood, ash accumulates. At first, there is plenty of wood and just a little ash. But over time, the ratio shifts, more ash, less wood. The fire burns in a smaller and smaller space as the ash takes up more room. Stars do the same thing. The core slowly fills with helium. The hydrogen burning happens in a thinner and thinner shell around that helium core. The star is still shining, still on the main sequence. But the core is changing, preparing for what comes next. And eventually, after billions of years for a star like the Sun, the hydrogen in the core runs out completely. There is still hydrogen in the outer layers of the star, but the core is now pure helium, dead fuel, inert ash, and helium, at the temperatures and pressures of a normal main sequence star, doesn't fuse. It just sits there, heavy, inert, not producing energy, so the core is no longer generating the outward pressure that was balancing gravity. And gravity, patient gravity, which has been waiting for this moment since the star was born, begins to win. The core contracts, shrinks, gets denser, gets hotter. Not the end. There are still many stages to go, but the beginning, the moment when the star stops being what it was and starts becoming something else. Stars must die because they run out of fuel, because fusion can't continue forever, because gravity is patient and inexorable and will eventually reclaim everything. But here is the beautiful part. This is not a flaw in the design. It is the design. Stars are supposed to die. Their deaths are necessary for the universe to evolve, to create new things, to spread the elements they've forged across space. If stars didn't die, there would be no carbon, no oxygen, no iron, no planets, no life. The universe would be nothing but hydrogen and helium, the primordial elements from the Big Bang, unchanged and unchanging. Death is not a failure. It is a feature. It is how the universe creates complexity, diversity, beauty. Stars die because they must, and in dying, they give birth to everything else. Gravity is patient. It doesn't T-rush. It doesn't T-force. It just waits. For billions of years, a star holds gravity at bay with the energy of fusion. The outward pressure of heat and light exactly balances the inward pull of gravity. The star is in equilibrium, stable, unchanging. But gravity is always there, always pulling, always waiting for the moment when the fusion slows, when the fuel runs low, when the pressure drops. And gravity is inevitable. You can resist it temporarily, with energy, with pressure, with heat, but you can resist it forever. Eventually, gravity wins. It always wins. This isn't cruel. It is not malicious. It is just physics. Mass attracts mass. Objects with mass pull on each other. The more mass, the stronger the pull, and stars have a lot of mass. The Sun, for instance, contains 99.86% of all the mass in the solar system. Earth, Jupiter, all the planets combined, they barely a rounding error compared to the Sun's mass, and all that mass creates gravity, strong gravity, gravity that wants to pull every atom of the Sun into the center, crushing it down to a single point. The only thing stopping that from happening is fusion. The energy released by the Sun's core pushes outward with exactly the force needed to balance gravity's inward pull. But when the fuel runs out, when fusion stops, that balance is broken, and gravity, patient, inevitable gravity, begins to compress the core. Slowly at first, the core contracts gently, but as it shrinks, it gets denser, and as it gets denser, gravity gets stronger, and as gravity gets stronger, the compression accelerates. This is the beginning of the end, the core collapsing, gravity reclaiming what it has been denied for billions of years. And you might think this sounds violent, sudden, catastrophic, but it is not. Not at first. The collapse takes time. For a star like the Sun, this initial contraction of the core happens over tens of millions of years, slow by human standards, almost glacial by stellar standards. The star is changing, yes. Dying, yes, but slowly, gently, with the same patience it showed during its life. Gravity doesn't hurry, it just pulls, steadily, continuously, inevitably, and the star responds by contracting, heating up, transforming. There is a rhythm to this, a calmness. Gravity pulls. Temperature rises, new processes begin. The star doesn't fight it, doesn't resist, it just changes, adapting to the new conditions, finding new equilibriums, trying to stabilize in different forms. And through all of this, the star continues to exist, changed. Yes, dying, yes, but still there. Still, a ball of gas held by gravity, still shining, still participating in the universe. Gravity is inevitable. But inevitability does mean violence. It just means certainty, patience. The calm, steady progression toward an outcome that was written into the initial conditions. The star will collapse, but slowly, beautifully, with grace. Let's talk about time, because stellar death happens on timescales so vast that they almost impossible to comprehend. A human lifetime is about 80 years. Civilization has existed for maybe 10,000 years. Homo sapiens as a species has been around for about 300,000 years. That feels like a long time, but the Sun will spend 10 billion years on the main sequence. 10 billion. That is 10,000 million. If you counted one number per second, it would take you more than 300 years just to count to 10 billion. And that is just the Sun's main sequence lifetime. The calm, stable part, the dying process, from when the Sun leaves the main sequence to when it becomes a white dwarf, will take another billion years or so. A billion years of slow transformation, of gradual change, of stages blending into each other. These timescales are so long that nothing we can relate to operates on them. Mountains rise and erode in tens of millions of years. Continents drift around Earth in hundreds of millions. But stars measure their lives in billions, and the universe itself is only 13.8 billion years old. The Sun, at 4.6 billion years, has lived for a third of the universe's total age. It will live for another third before it dies. Why does this matter? Why think about timescales so vast? Because it puts everything in perspective. The things you worry about, deadlines, relationships, money, health, they exist on timescales of days, months, years, Even the biggest human concerns play out over decades at most. But the universe operates on entirely different scales. Stars live for billions of years. They die over millions. The processes we'll explore tonight: red giants, planetary nebulae, white dwarfs. They unfold so slowly that if you could watch them in real time, you'd see no change, nothing happening, just stillness. And there is something deeply calming about that. To remember that the universe has patience, that it is not in a hurry, that transformation happens slowly, inevitably, but without rush. Your day was busy, maybe rushed, full of urgency, but the stars don't rush, can't rush. They change at the pace determined by physics, by the slow processes of fusion and gravity and radiation. And as you lie here, breathing slowly, letting your body relax, you are participating in the universe's patience. You are slowing down, moving from the frantic timescale of human life to something closer to cosmic time. Not billions of years, of course, just hours, but hours where nothing urgent needs to happen, where you can let time stretch, where you can stop measuring minutes and just exist, the way stars exist, present in the moment, not worried about tomorrow. The stars have been here for billions of years. They'll be here for billions more. And tonight, for a few hours, you can rest in the same kind of timelessness. No rush, no urgency. Just the slow, patient passage of time. The stars are dying, but so slowly that it looks like forever. Something strange happens when a star runs out of hydrogen in its core. Something that seems contradictory, paradoxical. The core gets smaller, but the star gets bigger, much bigger. Here is how it works. When hydrogen fusion stops in the core is now pure helium, inert, not producing energy. Without that energy pushing outward, gravity compresses the core. It shrinks, gets denser, gets hotter, and as the core contracts and heats up, it starts to heat the hydrogen in the shell of material surrounding it. That shell of hydrogen, now exposed to higher temperatures, begins fusing. Not in the core. The core is done with hydrogen, but in a thin shell around the core. This shell fusion actually produces more energy than the core did during the star's main sequence phase. More heat, more light, more outward pressure. And that extra energy pushes the star's outer layers outward. They expand, swell, grow. The star becomes a red giant. Our Sun, currently about 865,000 miles in diameter, will swell to perhaps 100 million miles across. When it becomes a red giant, it will grow more than 100 times its current size. Large enough to swallow Mercury, large enough to swallow Venus, large enough to possibly reach Earth's orbit. Imagine that. The Sun expanding so far that Earth, if it still exists, if it hasn't been vaporized, will be inside the Sun's outer atmosphere. And yet, despite being so much larger, the red giant Sun will be cooler at its surface. Red giants are red because they cooler than main sequence stars. The surface temperature drops to maybe 3000 Kelvin compared to the Sun's current 5800 Kelvin. Cooler surfaces glow red, not yellow, hence the name. So the star is simultaneously contracting and expanding, the core getting smaller, denser, hotter, the outer layers getting larger, more diffuse, cooler. The star is transforming, reorganizing, finding a new equilibrium, and this happens slowly. For a star like the Sun, the transition from main sequence to red giant takes tens of millions of years. You wouldn't see the change from one year to the next, or even from one millennium to the next. But over millions of years, the change would be unmistakable. The star swells. Its color shifts from yellow to orange to red. Its luminosity increases. Red giants can be hundreds or even thousands of times brighter than they were on the main sequence, despite being cooler, simply because they so much larger. And through all of this, the star is still a star. Still fusing hydrogen, just in a shell instead of the core. Still shining, still radiating energy into space. It is dying, yes. This is the beginning of the end, but it is a slow death. A transformation, a change from one form to another. The star is becoming something it was, something larger, cooler, brighter, something beautiful and temporary and transitional. The red giant phase is the star's old age, and like human old age, it comes with both losses and strange new gifts. Let's imagine it. 5 billion years from now, The Sun has exhausted the hydrogen in its core. It is beginning its transformation into a red giant. From Earth, if Earth still exists, you'd notice the Sun getting gradually larger in the sky. Over millions of years, it would swell from the familiar disk you know to something enormous, covering more and more of the sky, growing from a circle you can block with your thumb to something that dominates the horizon. The sky would turn redder. The Sun's light, once yellow-white, now shifts to orange, then deep red. Daylight takes on a strange dusky quality, like permanent sunset. The world is bathed in red light, and it gets hotter, much hotter. As the Sun swells and brightens, Earth receives more energy, the oceans boil away, the atmosphere strips into space, the rocks melt. Earth becomes uninhabitable long before the Sun actually reaches it. Mercury, closest to the Sun, is consumed first, swallowed by the expanding solar atmosphere, then Venus, then possibly Earth, though some models suggest Earth's orbit might drift outward just enough to avoid being swallowed, leaving it as a scorched, airless rock, orbiting just outside the red giant's edge. Mars, further out, gets warmer. For a brief time, cosmically speaking, Mars might be warm enough for liquid water, but it is temporary. The Sun's red giant phase won't last long enough for life to evolve there. Just a brief window of warmth before the Sun moves on to its next stage. And the outer planets, Jupiter, Saturn, Uranus, Neptune, they receive more light, more heat. Their atmospheres might change. Their moons, especially Jupiter's moon, Europa, and Saturn's moon, Enceladus, which have subsurface oceans, might become more hospitable, or might lose their oceans to space. It is hard to predict, but through all of this, the Sun continues to shine, larger, redder, brighter than it ever was on the main sequence. It is pouring energy into space, fusing hydrogen in a shell around its helium core, burning the last of its fuel. And inside the core, gravity continues to compress. The helium ash gets denser and denser, hotter and hotter, building toward the next transformation. From a distance from another star system, from a planet orbiting a different sun, our solar system would look strange. A bloated red star where a yellow one used to be. The inner planets gone, the outer planets bathed in red light. But it wouldn't look unusual. This happens to every star like the Sun. Every solar system goes through this phase. Expected, just another stage in stellar evolution. The swollen Sun is beautiful, in its way. Enormous and red and luminous, dominating the solar system, shining with the last of its hydrogen fuel. It is dying, but it is dying brilliantly, taking its time, burning as bright as it can before the fuel runs out completely. Inside the red giant's core, pressure is building. The helium that accumulated during billions of years of hydrogen fusion is being compressed by gravity, squeezed, crushed, and as the core contracts, it heats up, temperature rises, density increases. The helium atoms are packed closer and closer together. And at a certain point, around 100 million Kelvin, something dramatic happens. The helium begins to fuse. Helium fusion is different from hydrogen fusion. It requires much higher temperatures. The helium nucleus has 2 protons, which repel each other with more force than hydrogen's single proton. You need extreme heat to overcome that repulsion and force helium nuclei to merge. But once it starts, it releases energy. 3 helium nuclei fuse to make 1 carbon nucleus. The process releases heat, light, and pressure, just like hydrogen fusion, but at higher temperatures. For stars like the Sun, low to medium mass stars. This helium fusion does start gradually. It starts suddenly, all at once, in what is called a helium flash. Here is why, in low-mass stars, the core gets so compressed during the red giant phase that the matter becomes degenerate. Degenerate matter is weird stuff. It is so compressed that quantum mechanical effects dominate. Electrons can't get any closer together. The matter is almost solid, almost incompressible. And in degenerate matter, when fusion starts, it doesn't regulate itself the way it does in normal stellar cores. In normal cores, if fusion gets too vigorous, the core expands, which cools it, which slows the fusion. A natural thermostat. But in degenerate matter, the core can expand easily. So when helium fusion starts, the energy release heats the core further, which makes fusion faster, which heats it more. A runaway reaction in a matter of seconds, literally seconds. The core releases as much energy as the entire galaxy. But, and this is important, this energy does blow the star apart. It is contained within the core. The outer layers of the star don't even notice. The helium flash happens deep inside, and the energy goes into breaking the degeneracy, expanding the core back to normal matter. Once the degeneracy is broken, the core can expand normally again, and the helium fusion settles into a steady, controlled burn. The star is now fusing helium in the core and hydrogen in a shell around the core. This is the horizontal branch phase. The star stabilizes again, not on the main sequence. It is past that, but in a new equilibrium, burning helium, producing carbon and oxygen, shining steadily. The helium flash is violent in terms of energy released, but it is hidden, internal. From the outside, the star barely changes. It might dim slightly as the core reorganizes, but there is no explosion, no visible drama. Just an internal transformation, a sudden shift from one state to another. And then the star continues, burning helium now, extending its life for a little longer. The flash lasts seconds, but it changes everything inside the star. It is the moment when death pauses, briefly, and the star finds a new way to shine. After the helium flash, the star enters a new phase of stability. It is burning helium in the core now, fusing it into carbon and oxygen. And this gives the star a reprieve, a temporary extension of its life. But it is brief, very brief compared to the main sequence. A star like the Sun will spend about 10 billion years burning hydrogen on the main sequence, but it will spend only about 100 million years burning helium, 1/100th as long. Why so short? Because helium fusion produces less energy per gram of fuel than hydrogen fusion. And there is less helium than there was hydrogen to begin with. The star is running on reserves now, burning the ash of its previous life, and those reserves won. But for those 100 million years, the star is stable again. The helium burning in the core produces energy. That energy balances gravity. The star shines steadily. From the outside, you might not even realize the star is dying. It looks normal, shining, stable, just doing its thing. But inside, the core is slowly filling with carbon and oxygen, the ash of helium fusion. And just like before, this ash doesn't burn. It just accumulates, layer by layer, atom. The star is running out of fuel again. Slower this time, but inevitably, and there is a pattern here. Hydrogen burns, produces helium. Helium accumulates, eventually burns, produces carbon. Carbon accumulates. And if the star is massive enough, carbon will eventually burn, producing heavier elements, and so on, up the periodic table. But our Sun isn't massive enough for that. It can heat its core enough to fuse carbon, so carbon just accumulates. The core fills with carbon and oxygen, the final products of the Sun, S-fusion. And when the helium runs out, when the core is pure carbon and oxygen, there is no next step, no next fusion process. The Sun has reached the end of its fusion life. The core, full of inert carbon and oxygen, begins to contract again. Gravity, patient as always, resumes its compression. The core shrinks, gets denser, gets hotter, but not hot enough to fuse carbon, just hot enough to heat the layers around it, where some helium and hydrogen still remain. These shells fuse vigorously, producing enormous amounts of energy, and that energy pushes the outer layers of the star outward again. Further than before, the star swells even larger, becomes an even bigger red giant, technically called an asymptotic giant branch star, but still just a very large, very red, very luminous star. This is the star's final phase before death, the last gasp, the final shedding of its outer layers before the core is exposed. The helium burning phase was a reprieve, a pause, a chance for the star to stabilize one more time before the final transformation. But it is over now. The fuel is gone. The core is inert. And the star must face what comes next. As the star enters its final red giant phase, the asymptotic giant branch, it becomes unstable. The outer layers start to pulsate. expand and contract, breathe in a sense. This happens because the star is now fusing in two thin shells, hydrogen in the outer shell, helium in the inner shell. And these shells don't burn steadily. They pulse. The helium shell will burn vigorously for a while, heating the layers above it, pushing them outward. But as the layers expand, they cool and the fusion slows. The pressure drops, the layers contract, the heating resumes. The cycle repeats. These are called thermal pulses, and they happen every few thousand to 100,000 years. Brief by stellar standards, but dramatic. During a thermal pulse, the star brightens significantly. Its outer layers expand. It might shed some mass into space, and then it contracts again, dims, settles down. From a distance, you'd see the star flickering, brightening and dimming on timescales of thousands of years, pulsating like a slow heartbeat. Some stars pulsate so regularly that we call them variable stars. Cepheid variables are our Lyrae stars. They're all stars in late stages of evolution, pulsating with clockwork regularity. Astronomers use these variable stars as standard candles to measure distances in the universe. The period of pulsation correlates with the star's intrinsic brightness, so by watching how fast a star pulsates, we can calculate how bright it really is. And by comparing that to how bright it appears, we can calculate how far away it is. So these dying stars pulsating, unstable, shedding mass, are actually incredibly useful to science. They help us map the universe, measure cosmic distances, understand the scale of the galaxy. But from the star's perspective, the pulsations are signs of instability, of structures breaking down, of the approach of final death. The outer layers are barely held by gravity anymore. They're so far from the core, remember, the star has swollen to enormous size, that the gravitational pull is weak, and every pulse sends waves of pressure outward, pushing the outer layers further away. Eventually, the star will pulse so hard that the outer layers escape entirely. They'll drift into space, expanding away from the core, leaving the hot, dense center exposed. But we're not there yet. For now, the star is pulsating, breathing, flickering between brighter and dimmer states. The outer layers billowing like curtains in a breeze. It is beautiful, in a way. The star is unstable, yes. Dying, yes. But the pulsations create a rhythm, a pattern, a kind of cosmic breathing that will continue for tens of thousands of years before the final shedding begins. The star is restless, moving, changing, unable to find a stable state anymore, because there is no more fuel to stabilize on. Gravity pulls inward, pressure pushes outward, and the star oscillates between the two, unable to settle, unable to find equilibrium. It is the restlessness of old age, the final stage before the letting go. There comes a moment when the star can no longer hold on. The outer layers, pulsating and billowing, finally break free from the star's weak gravitational grip. They drift into space, slowly expanding, creating a shell of gas surrounding the core. This is not an explosion. It is not violent. It is more like exhaling, breathing out, releasing. The star gently pushes its outer layers away, and they go willingly, drifting outward at maybe 10 to 20 miles per second, fast by human standards, but slow for cosmic processes. The gas expands in a graceful, gradual way, spreading out over thousands of years, and what is left behind? The tiny, hot, dense center of what used to be a star. The carbon-oxygen core that was hidden beneath all those layers of hydrogen and helium. This core is now exposed to space. It is incredibly hot, over 100,000 Kelvin at the surface, and it is incredibly bright, despite being small, about the size of Earth. But as luminous as the sun was on the main sequence, the light from this exposed core shines outward through the expelled gas, and the ultraviolet radiation from the core ionizes that gas, strips electrons from atoms, exciting them, making them glow. And this glowing shell of gas is what we call a planetary nebula. The name is misleading. It has nothing to do with planets. Early astronomers, looking through small telescopes, saw these round, fuzzy objects and thought they looked like planets, so they called them planetary nebulae. The name stuck, even though we now know they re nothing like planets. They re the cast off outer layers of dying stars, shells of glowing gas, expanding slowly into space, lit from within by the hot core at the center. And they re-beautiful some of the most beautiful objects in the universe. The Ring Nebula, the Helix Nebula, the Cat SI Nebula. Each one unique, each one a different color and shape, each one the signature of a star letting go. The colors come from different elements in the gas. Oxygen glows blue, green. Hydrogen glows red. Nitrogen glows red, orange. The mix of colors depends on what elements the star created during its lifetime and how the ultraviolet light excites them, and the shapes vary wildly. Some planetary nebulae are round and symmetric like bubbles. Others are elongated, like cylinders or hourglasses. Some have complex structures, multiple shells, jets, knots of denser gas. We're still figuring out what causes these shapes. Maybe magnetic fields, maybe rotation, maybe binary companions. Many dying stars have partner stars that affect how the gas is expelled. But regardless of the mechanism, the result is beauty. Dying stars create some of the most visually stunning objects in the cosmos. The star is letting go, releasing what it no longer needs, shedding layers that served their purpose during the star's life but are now just weight, just gravity's burden, and in letting go, the star creates art. 2000 light years from Earth, in the constellation Lyra, there is a planetary nebula called the Ring Nebula, also known as M57, Messier 57. After the French astronomer who catalogued it, through a small telescope, it looks like a smoke ring, a perfect circle of glowing gas floating in space. Pale green with a darker center, and if you look closely, a tiny white dot in the middle, the exposed core of the star that created it. The Ring Nebula is about 1 light year across. That shell of glowing gas has been expanding for about 6,000 to 8,000 years since the star expelled it. It is still expanding now at about 12 miles per second, spreading slowly outward into the interstellar medium. The gas is thin, thinner than any vacuum we can create on Earth, but it glows because it is ionized by the radiation from the central star. Each atom absorbs a photon of ultraviolet light, gets excited, and then releases that energy as visible light. The green color comes from doubly ionized oxygen atoms that have lost 2 electrons. The red outer regions come from hydrogen and nitrogen. The mix creates a gradient, a rainbow of colors that shifts from green at the center to red at the edges. And if you could see the Ring Nebula with eyes sensitive to all wavelengths, not just visible light but also ultraviolet and infrared, you'd see even more structure. Knots and filaments, shells within shells. The nebula isn't smooth, it is textured, complex, full of detail. The central star, the white dwarf that will be the final remnant, is incredibly hot, about 120,000 Kelvin, hot enough to ionize the gas around it, hot enough to shine with intense ultraviolet light, but it is also tiny, about the size of Earth, incredibly dense. A teaspoon of its material would weigh thousands of pounds. The star is almost done dying. It has expended all its fusion fuel, expelled its outer layers. Now it is just cooling, slowly radiating away its heat into space. Over the next hundreds of thousands of years, a white dwarf will cool. The nebula will expand, spreading out until it is so thin it is no longer visible. The gas will mix with the interstellar medium, enriching it with carbon and oxygen and nitrogen, elements the star created during its life. And eventually, millions of years from now, the Ring Nebula will fade into invisibility. The white dwarf will cool to a black dwarf, a cold, dark ember of a star, no longer shining, just a lump of carbon and oxygen floating in space. But for now, the Ring Nebula glows. It is visible from Earth with a modest telescope. You can see it yourself on a clear night if you know where to look. A dying star 2000 light, years away, glowing gently in the darkness. A reminder that death can be beautiful, that endings can create light. The Ring Nebula is a gentle goodbye, a star. No 2 planetary nebulae look the same. Each one is unique, shaped by the particular conditions of the star that created it. Some are round, like perfect bubbles. The Dumbbell Nebula, the Helix Nebula, they're roughly spherical, with the gas expanding evenly in all directions. Others are elongated. The Hourglass Nebula looks like, well, an hourglass, 2 lobes of gas extending in opposite directions. connected by a thin waist. The red rectangle is even more extreme, with a nearly perfect rectangular outline, and some are wildly complex. The Cat's Eye Nebula has at least 11 concentric shells, suggesting the star expelled material in multiple pulses over thousands of years. The Eskimo Nebula has a bright inner region surrounded by a complex system of filaments and knots. What creates these shapes? We're still figuring it out, but several factors seem to matter: rotation. If the star is spinning, the gas might be expelled more easily at the poles than at the equator, creating bipolar shapes, two lobes extending in opposite directions. Magnetic fields. The star's magnetic field might channel the gas along field lines, creating jets or filaments. Binary companions. Many dying stars have companion stars. The companion's gravity can distort the gas flow, creating asymmetries, spirals, or complex patterns. Stellar winds. Before the planetary nebula phase, the star might have lost mass through stellar winds, streams of gas flowing off the surface. These winds can carve shapes in the subsequently expelled material. The result is an incredible diversity of forms. Some nebulae look like flowers, some like butterflies, some like eyes, hourglasses, spirals, spheres, cylinders. Each one a unique sculpture carved by physics and time, and the colors add to the beauty. Planetary nebulae glow in shades of green, blue, red, pink, yellow. The specific mix determined by which elements are present and how they're ionized. Oxygen, the most common element after hydrogen and helium, glows green and blue. Hydrogen glows red, nitrogen glows red, orange sulfur glows red. Helium can glow in several colors depending on its ionization state. Astronomers create images of nebulae by taking pictures in different wavelengths and assigning each wavelength a color. Oxygen might be assigned blue, hydrogen red, nitrogen green. The resulting images are false color. They don't represent what your eye would see, but they reveal the nebula's composition and structure, and the images are stunning. Some of the most iconic pictures from the Hubble Space Telescope are of planetary nebulae. The vivid colors, the intricate shapes, the sense of structure and pattern, they're mesmerizing. These are dying stars, objects in the process of disintegrating, dissolving into space, and yet they create some of the most beautiful structures in the universe. Beauty from death, color from endings, structure from chaos. The planetary nebulae remind us that transformation doesn't have to be ugly, that letting go can create something worth looking at. The nebulae glow for a few tens of thousands of years. A blink, cosmically. But during that blink, they shine with colors and shapes that inspire awe in anyone who sees them. The planetary nebula isn't just beautiful, it is functional. It serves a purpose in the galaxy's ecology. All the gas that is being expelled into space, the shell of material glowing around the white dwarf, is enriched with heavy elements: carbon, nitrogen, oxygen, neon, magnesium, elements that didn't exist when the star was born. Remember, the star began as mostly hydrogen and helium, the primordial elements from the Big Bang. That is what it was made of. That is what it had to work with. But during its lifetime, the star fused hydrogen into helium, helium into carbon and oxygen. It created new elements through nuclear fusion in its core. And now, as it dies, it is returning those elements to space. The carbon and oxygen from the core, mixed into the outer layers during the star's pulsating phase, are now spreading through the galaxy. This material will mix with the interstellar medium, the thin gas between the stars. It will drift, spread, cool, condense, and eventually it will collapse under gravity to form new stars. And those new stars will be richer in heavy elements than the previous generation. They'll have more carbon, more oxygen, more of the building blocks needed to make planets, life, complexity. Earth exists because of this process. The carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was created in stars, forged in stellar cores during fusion, expelled during planetary nebula phases or supernova explosions, drifted through space, condensed into a new solar system, became planets, became you. You are made of recycled star material. Your atoms were inside stars that died billions of years ago, long before the sun or Earth existed. And someday, the sun will do the same. It will create carbon and oxygen. It will expel them in a planetary nebula. That material will drift through the galaxy for billions of years, and maybe eventually it will become part of a new planet orbiting a new star, and new life will arise, made partly of atoms that are currently inside the sun. The cycle continues. Stars form from gas clouds. They shine. They create heavy elements. They die and return those elements to space. New stars form from the enriched gas. They create more heavy elements. They die. The cycle repeats, each generation slightly richer in heavy elements than the last. This is how the galaxy evolves, how complexity builds, how we got from a universe of pure hydrogen and helium to one with planets and oceans and life. The planetary nebula is part of this. It is not just a beautiful object. It is a delivery system, a way for dying stars to give back to the galaxy, to ensure that their deaths are not endings but contributions. The gas glows for a while, visible and beautiful, and then it fades, disperses, becomes part of the raw material for the next generation. Death feeds life, endings enable beginnings. The stars know this. They accept it. They participate in it willingly. Planetary nebulae are temporary. They don't last long, not by cosmic standards. The gas shell is expanding at about 10 to 20 miles per second, fast but finite. And as it expands, it spreads out, gets thinner, more diffuse. Initially, the shell is dense enough and the central star hot enough that the gas glows brightly. You can see it from thousands of light years away. It is one of the most luminous objects in the sky, despite being just a thin shell of gas. But over time, several things happen. First, the gas continues to expand. After 10,000 years, it might be a light year across. After 100,000 years, several light years, the expansion dilutes the gas, making it thinner and thinner. Second, the central star cools. Remember, it is no longer fusing. It is just a hot ember, radiating away its stored heat. As it cools, it emits less ultraviolet radiation, and less UV means less ionization, which means the gas glows less brightly. Third, the gas starts to recombine. Electrons that were stripped away by ionization start to rejoin their atoms. The gas becomes neutral again, and neutral gas doesn't glow the way ionized gas does. All of these processes happen gradually over tens of thousands of years. The nebula slowly dims, fades, spreads out. After about 20,000 to 50,000 years, most planetary nebulae are no longer visible. The gas has expanded so much and dimmed so much that it blends into the background glow of the interstellar medium. It is still there, the atoms don't disappear, but you can see it as a distinct nebula anymore. And the white dwarf in the center continues to cool. After about 100,000 years, it is cooled enough that it is no longer ionizing any gas. It just sits there, a slowly cooling ember in space. So the planetary nebula phase is brief. A flash, cosmically speaking. The star spent billions of years on the main sequence, hundreds of millions burning helium, and then just a few tens of thousands of years as a glowing nebula. But what a flash! During those tens of thousands of years, the nebula is visible across the galaxy. It is beautiful. It is inspiring. It is a marker of stellar death that can be seen and studied and appreciated. And then it fades. The gas disperses. The star cools. And all that remains is the white dwarf, the final remnant of the star's core, quietly radiating away its remaining heat. The nebula doesn't last, but while it does, it is magnificent. A temporary burst of beauty in the long, slow process of dying, and maybe that is okay. Not everything needs to last forever. Some things are beautiful precisely because they are temporary, because they glow brightly for a while and then fade, making room for the next generation. The planetary nebula lasts just long enough to be noticed, to be remembered to contribute its enriched gas to the galaxy, and then it lets go, disperses, becomes part of the background, beautiful, brief, purposeful, and then gone. After the planetary nebula fades and disperses, what remains is the core, the tiny, dense, incredibly hot center of what used to be a star. This is a white dwarf. It is about the size of Earth, roughly 8,000 miles in diameter. But it contains as much mass as the Sun. Imagine compressing the entire mass of the Sun into a sphere the size of our planet. The density is staggering. A teaspoon of white dwarf material would weigh about 15 tons on Earth. The white dwarf is made of carbon and oxygen, mostly the ash of helium fusion, compressed into a solid-like state by gravity. It is not actually solid in the way you think. It is still incredibly hot, over 100,000 Kelvin at the surface initially. But it is not a gas either. It is something in between, something quantum mechanics calls degenerate matter. In degenerate matter, electrons are packed so close together that quantum effects dominate. Electrons can occupy the same quantum state, so they reforced into higher and higher energy levels. This creates a pressure, degeneracy pressure, that has nothing to do with temperature. It is purely quantum mechanical. And this degeneracy pressure is what holds the white dwarf up against gravity. There is no fusion anymore, no heat being generated, just the quantum mechanical resistance of electrons being compressed too close together. The white dwarf is stable as it can be. Gravity pulls inward. Degeneracy pressure pushes outward. They balance. The white dwarf will maintain this size essentially forever, but it is hot, incredibly hot, and it is slowly radiating that heat into space. When you are hot and you are in the cold vacuum of space, you cool down. You radiate heat as light, infrared, visible, ultraviolet, depending on your temperature. And since space doesn't provide any new heat, you just keep cooling. Forever, the white dwarf starts at over 100,000 Kelvin. It glows blue, white, incredibly bright despite its small size. Over millions of years it cools to 50,000 Kelvin, still very hot, still bright. Over billions of years it cools to 10,000 Kelvin, still hot enough to glow white. Hence the name white dwarf, a small, white, incredibly dense star remnant, and it keeps cooling. 5,000 Kelvin, 3,000 Kelvin. The color shifts from white to yellow to orange to red as the temperature drops. But the cooling is slow, incredibly slow, because the white dwarf is small and dense. It has a small surface area relative to its mass, and heat escapes through the surface. Small surface area means slow cooling. It will take trillions of years for a white dwarf to cool completely. Trillions, thousands of billions. The universe is only 13.8 billion years old. No white dwarf has had time to cool to absolute zero yet. Every white dwarf that is ever formed is still glowing, still warm, still radiating. The white dwarf is the final resting state of stars like the sun. Not dead, exactly. Still glowing, still existing, but no longer alive in the sense of fusing, changing, evolving. Just cooling, slowly, patiently. Let's talk about what white dwarfs are made of, because it is genuinely strange. Degenerate matter doesn't behave like normal matter. It follows different rules. In normal matter, like the air around you, or the star during its main sequence, life atoms are separated by relatively large distances. There is space between them, and temperature determines pressure. Heat the gas, and the atoms move faster, collide more often, create more pressure. But in degenerate matter, the atoms are crushed so close together that the electrons, the negatively charged particles orbiting atomic nuclei, are forced into proximity with each other. And electrons really don't like being close to other electrons. There is a quantum mechanical principle called the Pauli exclusion principle. It says that no two electrons can occupy the same quantum state, the same energy level, the same position, the same momentum at the same time. In normal matter, this isn't a problem. There is plenty of room. Electrons can spread out, occupy different states, avoid each other. But in degenerate matter, there is no room. Every low-energy state is occupied. If you want to add more electrons or compress the matter further, the new electrons have to go into higher energy states. They're forced to move faster to have more momentum just to comply with the exclusion principle, and this creates pressure, degeneracy pressure. It is not related to temperature. You could cool degenerate matter to absolute zero, and the pressure would remain the same because it is not about thermal motion. It is about quantum states being filled. This is what holds white dwarfs up. Gravity wants to compress the star further, but the electrons are already packed as tightly as quantum mechanics allows. They can't get closer. They resist, not because they're hot, but because the laws of physics literally prevent them from occupying the same space. It is a strange kind of solidity. The white dwarf is sometimes described as a quantum solid or a metallic crystal. The carbon and oxygen nuclei are arranged in a lattice, like a crystal, while the electrons form a degenerate gas permeating the lattice. It is neither liquid nor solid nor gas in the normal sense. It is something that only exists under extreme conditions, conditions found in the cores of dead stars. And this state is stable. The white dwarf will remain in this configuration essentially forever. The degeneracy pressure doesn't weaken as the star cools. It doesn't decay. It just is a permanent feature of matter compressed to these densities. So the white dwarf sits in space, supported by quantum mechanics, cooling slowly, not because it is burning anything, but just because it is radiating away its stored heat. A star held up not by heat or pressure from fusion, but by the quantum mechanical property of electrons, the universe running on rules that seem abstract and theoretical, until you realize they're what is keeping dead stars from collapsing. The white dwarf is a quantum object, a macroscopic planet-sized manifestation of subatomic rules. Strange, beautiful, stable. It doesn't need to do anything. It doesn't need to change. Just exists, held by physics, cooling in the dark. The brightest star in Earth's night sky is Sirius. It is actually a binary system, two stars orbiting each other. Sirius A is the bright one you can see with your naked eye, but orbiting it every 50 years is a small, faint companion. Sirius B is a white dwarf. It is about the size of Earth, but it contains almost as much mass as the Sun. When it was discovered in 1862, it was the first white dwarf ever observed. Astronomers had theorized about such objects, but Sirius B was the proof, a star with enormous mass packed into a tiny volume. Initially, astronomers were baffled. How could something so small be so massive? It didn't fit their understanding of how stars worked. The density seemed impossible. But as quantum mechanics developed in the early 20th century, scientists realized that white dwarfs were supported by degeneracy pressure. The mystery was solved. Sirius B wasn't impossible. It was just quantum mechanical. Today, we know that Sirius B was once the more massive star in the system. It evolved faster than Sirius A, went through its red giant phase, expelled its outer layers. Meanwhile, Sirius A is still on the main sequence, still fusing hydrogen, still in its long middle age. But eventually, billions of years from now, Sirius A will also evolve into a red giant, and then a white dwarf. And the system will be two white dwarfs orbiting each other, slowly cooling, slowly fading, both of them remnants of what they used to be. From Earth, Sirius B is difficult to see. You need a good telescope and the right conditions to spot it. A tiny point of light very close to the brilliant glow of its companion. But it is there, a white dwarf orbiting every 50 years, following the same elliptical path it has followed for millions of years, slowly radiating away its heat. Sirius B is about 25,000 years old as a white dwarf. In cosmic terms, that is very young. It is still hot, about 25,000 Kelvin, still glowing white. Hot. It will stay visible for billions of years as it gradually cools. But the really remarkable thing about Sirius B is that it is so close to Earth, only 8.6 light years away, close enough that we can study it in detail, close enough that we can measure its temperature, its mass, its composition, close enough that it became the prototype for understanding white dwarfs. Every white dwarf in the galaxy is in some sense compared to Sirius B. It is our reference point, our nearby example of what happens to stars like the Sun when they die. And it is comforting, in a way, to know that even dead stars can have companions, that they can orbit together, locked in gravitational embrace, cooling slowly in each other's presence. Sirius B is not alone, and billions of years from now, neither will Sirius B. They'll both be white dwarfs, both cooling, both orbiting, both remnants of stellar lives well lived. Death doesn't have to mean solitude. There is a limit to how massive a white dwarf can be, a hard limit determined by physics, beyond which a white dwarf cannot exist. It is called the Chandrasekhar limit, named after Subramanian Chandrasekhar, the Indian-American astrophysicist who calculated it in 1930. He was 20 years old at the time, working out the math during a ship voyage from India to England. The limit is about 1.4 solar masses. If a white dwarf is less massive than this, degeneracy pressure can hold it up indefinitely. But if it is more massive than 1.4 times the Sun's mass, degeneracy pressure isn't T enough. Gravity overwhelms the quantum mechanical resistance of electrons, and the white dwarf collapses. What happens then depends on the situation. If the white dwarf is alone, it just can T-form a star more massive than 1.4 solar masses at the end of its life. 1. T become a white dwarf. It will collapse further into something else. A neutron star, perhaps, or a black hole. We'll get to those. But there is another scenario. Suppose you have a white dwarf that is below the Chandrasekhar limit, stable, happily cooling. But suppose it has a companion star, and suppose that companion is close enough that material from the companion can fall onto the white dwarf. Gas from the companion spirals down onto the white dwarf surface. It accumulates. The white dwarf gets more massive, slowly. Over thousands or millions of years, it accretes matter from its companion, and eventually it reaches the Chandrasekhar limit. At that point, the white dwarf can T-support itself anymore. Gravity wins. The core collapses suddenly, and the temperature spikes. The carbon and oxygen in the white dwarf, which weren't T-hot enough to fuse before, suddenly are. Carbon fusion begins. Explosively, the entire white dwarf, the whole Earth-sized ball of carbon and oxygen, detonates in a matter of seconds. The fusion releases so much energy that the white dwarf is completely destroyed, blown apart, vaporized. This is called a type ER supernova, a specific kind of supernova explosion that happens when white dwarfs exceed the Chandrasekhar limit. These explosions are incredibly bright as an entire galaxy for a few weeks. And they are incredibly useful to astronomers, because every type IR supernova has roughly the same intrinsic brightness. That makes them standard candles for measuring cosmic distances. But from the white dwarf's perspective, it is a catastrophic failure. The quantum support gives way. Gravity collapses the core. Fusion runs away. The star that spent billions of years slowly dying is destroyed in seconds. The Chandrasekhar limit is the line between quiet cooling and violent explosion, between the slow fade of the white dwarf and the sudden brilliance of supernova. Most white dwarfs never reach this limit. They reborn below it and stay below it, cooling peacefully forever. But some, those with companions, those accreting mass, approach the limit, and when they cross it, their quiet death becomes a violent one. The limit is absolute, unchanging, a fundamental property of how matter behaves under extreme compression. Imagine a white dwarf alone in space, no companion, no planetary nebula anymore. That faded millions of years ago. Just the small, dense core, glowing faintly, radiating its heat into the void. It has been cooling for 1 billion years. Its surface temperature has dropped from 100,000 Kelvin to 10,000 Kelvin. It glows a dull white like heated metal, but dimmer than it used to be, and it continues to cool. Another 1 billion years pass. The temperature drops to 5,000 Kelvin. The color shifts from white to yellow. Another 1 billion years, 3,000 Kelvin. The white dwarf now glows orange, like a dying ember in a fireplace. Time continues. The universe ages, galaxies evolve, stars are born and die around the white dwarf. But the white dwarf just cools, patient, unhurried. After 10 billion years, longer than the current age of the universe, the white dwarf might be down to 1,000 Kelvin. Still warm by human standards, but cold for a star. It glows a dull red, barely visible, and still it cools. The process is asymptotic. The white dwarf approaches absolute zero but never quite reaches it. There is always some heat left, always some faint glow, just less and less as time goes on. After 1 trillion years, 1,000 billion, far longer than the universe has existed, the white dwarf is almost invisible, still warm, maybe a few hundred Kelvin, but too dim to see except with the most sensitive instruments. After 10 trillion years, it is essentially black. A black dwarf, a lump of crystallized carbon and oxygen, cold, dark, inert, no longer glowing at all, just existing. This is the final state of stars like the Sun. After all the fusion, all the red giant phases, all the planetary nebulae and glowing embers. Eventually, just a cold, dark crystal, Earth, dense beyond imagining, but dark. The universe isn't old enough for black dwarfs to exist yet. Every white dwarf ever formed is still glowing, still warm. But given enough time, trillions of years, they'll all cool to darkness, and they'll remain. Black dwarfs don't decay. They don't collapse further. They don't change. They just sit in space forever, dark and cold and stable. It is the quietest possible ending. No explosion, no drama. Just a slow fade from bright to dim to dark, over timescales longer than we can meaningfully imagine. And there is something peaceful about that. About the idea that after all the changes, all the transformations, the star finally reaches a state where it can just be, no more evolution, no more processes, just existence. The white dwarf becomes a black dwarf. The cooling completes. The star has died its final death, not into non-existence, but into permanent, unchanging rest. Still atoms arranged in a crystalline lattice, still possessing mass and gravity and presence, but no longer shining, no longer changing, just resting in the dark, patient, and permanent, for the rest of time. Everything we've discussed so far, the red giant phase, the planetary nebula, the white dwarf, applies to stars like the Sun, low to medium mass stars, stars between about 0.8 and 8 times the Sun's mass. But more massive stars die differently. Their deaths are more violent, more complex, more dramatic. The key is temperature. More massive stars have stronger gravity, which compresses their cores more, which makes them hotter, and hotter cores can fuse heavier elements. A star like the Sun can fuse hydrogen into helium, and helium into carbon and oxygen. That is it. The core never gets hot enough to fuse carbon, but a star 10 times the Sun's mass. Its core can reach the temperatures needed for carbon fusion. Carbon fuses into neon and magnesium, then neon fuses into oxygen and magnesium, then oxygen fuses into silicon and sulfur. Each stage produces heavier elements. Each stage requires higher temperatures. Each stage happens faster than the last. Hydrogen fusion lasts billions of years. Helium fusion lasts millions. Carbon fusion lasts thousands of years. Neon fusion lasts a few years. Oxygen fusion lasts months. Silicon fusion lasts days. The star is burning through its fuel faster and faster, creating heavier and heavier elements. In its core, the core develops a layered structure, like an onion. Hydrogen burning in the outermost shell, helium in the next shell inward, carbon, neon, oxygen, silicon, each in successive shells, all burning simultaneously. And at the very center, iron accumulates. Iron is the end of the line. It is the most stable nucleus. Fusing iron doesn't release energy, it consumes energy. So when the core becomes pure iron, fusion stops completely. There is no next step. The core is now about 1.5 times the mass of the Sun, made entirely of iron supported by electron degeneracy pressure, the same quantum pressure that holds up white dwarfs. But unlike a white dwarf, this iron core is surrounded by layers of still fusing material. The star is still generating enormous amounts of energy in those shells, and the iron core just sits there inert, growing as silicon fusion in the shell above it continues to add more iron. And then, when the iron core reaches about 1.4 solar masses, the Chandrasekhar limit, it can't support itself anymore. Degeneracy pressure fails, gravity wins, and the core collapses. Not slowly, not gently. In about 1 second, the core, 1.4 times the mass of the Sun, about the size of Earth, collapses to about 12 miles in diameter. 1 second, Earth, sized to city, sized. The most rapid collapse of matter in the universe. And when matter collapses that fast, that drastically, the results are catastrophic. The core rebounds, shock waves propagate outward. The star explodes. Supernova. This is how massive stars die. Not with a gentle exhalation of gas, not with a pretty nebula, with a violent explosive destruction that releases more energy in a few seconds than the star released during its entire previous life. Picture a massive star in the final moments before it explodes. It is enormous, perhaps 50 or 100 times the diameter of the Sun, and inside it is structured like an onion, with shells of different elements burning at different rates. The outermost layer is still mostly hydrogen, cool, relatively speaking, not fusing, just sitting there, part of the star's extended envelope. Deeper in, there is a shell where hydrogen is fusing into helium. This shell is hot, actively burning, producing energy. Deeper still, a shell of helium fusion, creating carbon and oxygen. Then carbon fusion, creating neon and magnesium. Then neon fusion, creating oxygen and magnesium. Then oxygen fusion, creating silicon and sulfur. Then silicon fusion, creating iron. And at the very center, the iron core, inert, growing, doomed. Each shell is operating on a different timescale. The hydrogen shell has been burning for millions of years, the helium shell for hundreds of thousands, the carbon shell for a few thousand years, the oxygen shell for a few months, the silicon shell for days. The star is rushing toward its end, each stage faster than the last, the core growing heavier with iron, approaching the limit. And the star has no idea, in the sense that stars can know anything. It is just following the laws of physics, fusing whatever it can fuse, burning through its fuel, building up the iron core that will be its doom. From the outside, the star looks normal, bright, massive, maybe a blue supergiant, depending on its mass and stage. There is no outward sign of the complex layered structure inside, no indication that the core is about to collapse. The star might have planets, might have asteroids and comets, and a whole solar system orbiting it, and they have no idea that in a matter of days or hours, their star is going to explode with the force of 1 billion suns. Inside, the silicon fusion continues. More iron accumulates in the core's mass approaches 1.4 solar masses, and then it reaches the limit. The core can't support itself anymore. Electron degeneracy pressure, which has been holding up the core, fails. The electrons can't resist gravity any longer. It happens fast, so fast that the outer layers don't have time to react. They still fusing, still burning, still operating normally. But the core beneath them is collapsing, falling inward, being crushed by gravity. Within a second, the core has collapsed from Earth, sized to about 12 miles across. The density spikes to unimaginable levels. The temperature reaches hundreds of billions of degrees. And the collapse halts suddenly as the core becomes incompressible. The matter has been squeezed so tightly that it can't be compressed further. The core rebounds, like a ball bouncing off the ground. The rebound sends a shock wave outward through the overlying layers, and the star explodes. All of this, the collapse, the rebound, the shock wave, happens in less than a second. After millions of years of steady burning, the star's death takes 1 second. Let us imagine the last day of a massive star's life, 24 hours before it becomes a supernova. At this point, the silicon shell has been fusing for about a week. The iron core has grown to nearly 1.4 solar masses. The star is in its final hours, though nothing visible suggests this. From a planet orbiting the star, if there is one, if it hasn't been vaporized during the star's red giant phase, everything seems normal. The star shines steadily, bright, massive, eternal, seeming. But inside, the silicon fusion is accelerating. The iron core is growing faster. The star is on a countdown. 12 hours before the explosion, the iron core is almost at the Chandrasekhar limit. The silicon shell is burning frantically. The inner structure is unstable, but still holding. 6 hours before, the core is so close to the limit that it is beginning to compress slightly. The density in the core is rising. But still, the degeneracy pressure holds 1 hour before. The core reaches 1.4 solar masses. Degeneracy pressure begins to fail. The core starts to contract, slowly at first, but accelerating. 10 minutes before, the core is collapsing noticeably. The silicon fusion above it is being disrupted, but the outer layers of the star haven't noticed yet. They re too far away. The star still looks normal from the outside. 1 minute before, the core is in free fall, collapsing faster and faster. The density is skyrocketing. The temperature is climbing toward 100 billion Kelvin. 10 seconds before, the core has collapsed to about 20 miles across. The collapse is approaching the speed of light. The iron nuclei are being crushed. Protons and electrons are being forced together, creating neutrons. 1 second before, the core has become incompressible. Pure neutrons, packed as tightly as matter can be packed. A collapse halts, the core rebounds, and then, now, the shock wave propagates outward. It tears through the silicon shell, through the oxygen shell, through carbon, helium, hydrogen, through all the layers of the star, moving at thousands of miles per shock wave rips the star apart. The outer layers, heated to billions of degrees by the shock, begin fusing explosively. The energy release is staggering, and the star explodes. From the outside, the change is sudden. One moment, a normal star. The next, a flash brighter than an entire galaxy. The star's brightness increases by a factor of 1 billion in a matter of hours. If you were on a planet orbiting this star, you wouldn't have time to notice. The explosion would vaporize the planet in seconds, turn it into plasma, scatter it into space. The last day of a massive star is just a normal day until the final second, when everything changes. There is no warning, no countdown, just normalcy until the moment of catastrophic collapse. And then, light, incredible, blinding, galaxy, outshining light. You might wonder, why do massive stars die so much faster than low-mass stars? A star 50 times the Sun's mass has 50 times as much fuel. You'd think it would last 50 times longer, but actually it lasts about 100 times less long. The Sun will live for about 10 billion years. A 50 solar mass star will live for about 5 million years. The more massive star has more fuel, but it burns through that fuel at a vastly higher rate. Why? Because massive stars have stronger gravity. Their cores are more compressed. More compression means higher temperature. Higher temperature means faster fusion. But it is not a linear relationship. A small increase in temperature causes a huge increase in fusion rate. The fusion rate goes roughly as temperature to the 4th power for hydrogen fusion. Double the temperature, and fusion happens 16 times faster. Massive stars have cores that are much hotter than the Sun. The Sun's core is about 15 million Kelvin. A massive star's core might be 30 or 40 million Kelvin. That difference means fusion happens hundreds or thousands of times faster. So massive stars burn bright and die young. They reprofligate with their fuel. They fuse hydrogen so fast that they run out in a few million years instead of billions. And because they burn so hot, they can fuse heavier elements. They have the temperature and pressure needed to fuse carbon, neon, oxygen, silicon, elements the Sun will never be able to fuse. This is both a blessing and a curse. The blessing is that massive stars create heavy elements, all the elements heavier than iron, gold, silver, uranium, platinum, are created in supernovae. If massive stars didn't exist, if they didn't burn hot and die violently, those elements would exist either. The curse is that massive stars don't last. They live fast, burn bright, and explode. They don't get the slow, graceful death of low-mass stars. They don't get billions of years of stability. They get a few million years of frantic burning followed by catastrophic collapse. But maybe that is okay. Maybe different types of stars serve different purposes. Low-mass stars provide stable, long-lived sources of energy. They are the patient, reliable stars that can support life on planets for billions of years. Massive stars are the element factories, the cosmic alchemists. They take hydrogen and helium and transmute them into carbon, oxygen, iron, and everything heavier. They enrich the galaxy with the elements needed to make planets and life. And then they die, scattering those elements across space in supernova explosions, seeding the galaxy with raw materials for the next generation of stars and planets. Each type of star has its role. Low-mass stars last. Massive stars create. Both are necessary. Both are necessary. Both contribute to the evolving complexity of the universe. The massive stars burn fast because they must. Their deaths are violent because violent deaths scatter elements far and wide. It is not a flaw in the design. It is the design. Massive stars come in many varieties. Unlike low-mass stars, which all follow roughly the same evolutionary path, massive stars can take many different routes through their lives and deaths. Blue supergiants are massive stars that are still relatively young. still on or near the main sequence. They re-hot, surface temperatures of 20,000 to 50,000 Kelvin, and they glow blue, white. Rigel in Orion is a blue supergiant, about 20 times the Sun, S mass, 40,000 times as luminous. Red supergiants are massive stars that have left the main sequence and swollen enormously. Their cores have run out of hydrogen and they've expanded, cooling their surfaces. Betelgeuse in Orion is a red supergiant, perhaps 15 to 20 times the Sun, S mass, but hundreds of times larger in diameter. If you put Betelgeuse where the Sun is, it would extend past Mars' orbit. Luminous blue variables are massive stars in a particularly unstable phase. They pulsate, vary in brightness, and sometimes eject huge amounts of mass in eruptions. Eta Carinae is a luminous blue variable, perhaps 100 times the Sun, S mass, and so luminous it is one of the brightest stars in the galaxy. It had a major eruption in the 1840s, ejecting several solar masses of material. Wolf. Rayet stars are massive stars that have lost their outer hydrogen layers entirely, exposing the helium and heavier elements beneath. They have extremely hot surfaces, 50,000 to 200,000 Kelvin, and strong stellar winds that continue to strip away mass. They on the brink of supernova. Each of these types represents a different stage or different evolutionary path for massive stars. Some massive stars go through all these phases in sequence. Blue supergiant to red supergiant to wolf, ray to supernova. Others skip stages or take different routes depending on their mass, composition, and rotation rate, and all of them will eventually explode. Whether they die as red supergiants or blue supergiants or wolf, rayet stars, the end is the same. Core collapse, supernova, explosion. The diversity is beautiful. Each massive star is an individual, with its own history, its own characteristics, its own path through life. They varied, complex, unpredictable in their details, even if their general fate is sealed. And they rare. Massive stars represent only a tiny fraction of all stars, maybe 0.1% or less. Most stars are small, dim red dwarfs. But massive stars are important beyond their numbers, because they so luminous, and because they create heavy elements. A single massive star might outshine 1,000,000 red dwarfs. A single supernova might enrich the interstellar medium with more heavy elements than 1,000 low mass stars could produce. So even though they rare and short-lived, massive stars shape the galaxy. They light it up. They create the elements that make planets and life possible. They die spectacularly, leaving behind neutron stars and black holes and expanding shells of enriched gas. The zoo of massive stars is rich and varied, and every one of them is headed, inevitably, toward a brilliant and violent end. The core has collapsed, rebounded. The shock wave is propagating outward through the star at thousands of miles per second. This is the beginning of a supernova. The shock wave carries enormous energy. As it moves through the overlying layers of the star, the silicon, oxygen, carbon, helium, hydrogen shells, it heats them to billions of degrees. And at these temperatures, fusion happens explosively. All the silicon that wasn't yet converted to iron fuses in seconds. All the oxygen fuses. Carbon, helium, even some of the hydrogen, everything fuses in a runaway reaction that releases staggering amounts of energy. This explosive fusion releases more energy in a few seconds than the star released during millions of years of normal fusion. The energy is so immense that it blows the entire star apart. The outer layers accelerate outward at a significant fraction of the speed of light, 10,000 miles per second, 20,000. The gas is heated to billions of degrees, ionized, shining with the intensity of 1 billion suns. Within hours, the supernova becomes visible from Earth. If it is close enough, and if anyone is watching, the star brightens dramatically, sometimes becoming bright enough to see during the day, certainly bright enough to be one of the brightest objects in the night sky. The brightness peaks within a few days, and then slowly declines over weeks and months. The star doesn't immediately disappear. It fades gradually as the expanding gas cools and spreads out. The explosion ejects most of the star's mass into space. The outer layers, all the hydrogen and helium and heavier elements created during the star's life, are scattered across light years. Only the core remains compressed into a neutron star, or, if the star was massive enough, collapsed into a black hole. The ejected material expands outward, forming what is called a supernova remnant. Over thousands of years, this expanding shell of gas will collide with the surrounding interstellar medium, creating shock waves, heating gas, compressing regions that might collapse to form new stars. The supernova has scattered the elements created in the star's core across the galaxy. Carbon, oxygen, silicon, iron, all the elements heavier than helium, created through fusion, are now drifting through space, ready to be incorporated into the next generation of stars and planets. This is how the galaxy is enriched, how the proportion of heavy elements slowly increases over time. Each supernova adds to the galactic reservoir of carbon, oxygen, iron, and heavier elements. And supernovae also create elements that can't be made in normal fusion. Elements heavier than iron, gold, platinum, uranium are created in the extreme conditions of the supernova explosion. The rapid neutron capture during the explosion creates these heavy elements and scatters them into space, along with everything else. So a supernova is not just destruction, it is creation. It is the universe's way of building complexity, of creating the raw materials for planets and life. The star died violently, but its death was productive, necessary, beautiful in its own fierce way. A supernova at peak brightness can outshine an entire galaxy. Think about that. One exploding star shining brighter than 100 billion normal stars combined. For a few weeks, a supernova can be the brightest object in its galaxy. It can be brighter than all the other stars in that galaxy added together. From a distance, an entire galaxy might be reduced to a bright, featureless glow dominated by a single point of light, the supernova. In our own galaxy, we've seen a few supernovae over recorded history. The most famous was observed in 1054 AD by Chinese astronomers. They recorded a guest star in the constellation Taurus, bright enough to be visible during the day for weeks. That was a supernova, and the remnant, the expanding shell of gas it created, is now called the Crab Nebula. In 1572, Tycho Brahe observed a supernova in Cassiopeia. It was brighter than Venus, visible in daylight, and it challenged the prevailing belief that the heavens were unchanging. If stars could appear and disappear, the cosmos was more dynamic than anyone thought. In 1604, Johannes Kepler observed another supernova in Ophiuchus. It was the last supernova visible to the naked eye in our galaxy. Over 400 years ago now, we're overdue. Statistically, supernovae occur in our galaxy about once every 50 years, but most are obscured by dust or occur on the far side of the galaxy, where we can see them. We haven't seen a nearby naked eye supernova in over 4 centuries, but we see supernovae in other galaxies all the time. Modern telescopes detect dozens per year, each one a massive star exploding, each one briefly outshining its entire host galaxy. The brightness comes from the energy of the explosion and from the radioactive decay of nickel-56, created during the supernova. Nickel-56 decays into cobalt-56, which decays into iron-56, and each decay releases gamma rays that heat the expanding gas, making it glow. This radioactive decay is why supernovae fade gradually rather than winking out immediately. For weeks and months, the nickel keeps decaying, keeps heating the gas, keeps the supernova bright. But eventually, the nickel is exhausted and the remnant fades to invisibility. From Earth, watching a supernova in another galaxy, you see a new point of light appear. Over a few days, it would brighten, becoming one of the brightest stars in that part of the sky. And then, slowly, over weeks and months, it would fade, dimming until it disappeared below the threshold of visibility. The star lived for millions of years. It exploded in seconds, and it remained visible to us for months, a brief window when we could see the aftermath of stellar death from across the universe. The brightness is astonishing, a testament to the sheer energy released when a star dies violently. More energy in a few seconds than the star emitted during its entire life. A final, brilliant flash before the remnant fades into darkness. After the initial explosion, after the brightness fades, what remains is the supernova remnant, a vast expanding shell of gas plowing through the interstellar medium. The gas is moving fast, thousands of miles per second, and when it collides with the surrounding gas and dust, it creates shock waves. These shocks heat the gas to millions of degrees, making it glow in X-rays, visible light, radio waves. The Crab Nebula, remnant of the 1054 supernova, is still expanding. It is about 11 light years across now and still growing. At its center is a pulsar, a rapidly spinning neutron star that powers the nebula's glow. The nebula shines with a strange, mottled light dominated by blue and white regions where high-energy electrons spiral in magnetic fields. The Vela supernova remnant from a supernova about 11,000 years ago is enormous, 8 degrees across in the sky, 16 times the diameter of the full moon. It is so close and so large that we actually inside part of its expanding shell. We reliving within a supernova remnant surrounded by gas expelled when a massive star died before recorded history began. The Cygnus Loop, another ancient supernova remnant, is about 10,000 years old and spans 3 degrees of sky. It looks like delicate lacework, wispy filaments of glowing gas where the shock wave is interacting with dense regions of the interstellar medium. These remnants can last for tens of thousands of years before they fade into the background. Eventually, the expanding shell slows down, cools, mixes with the surrounding gas, and becomes indistinguishable from the general interstellar medium. But while they last, they re-beautiful, and they re-important. The shock waves from supernova remnants can trigger the collapse of nearby gas clouds, causing new stars to form. So supernovae don't just enrich the interstellar medium with heavy elements. They also trigger star formation, death leading directly to birth. The material ejected by the supernova, carbon, oxygen, silicon, iron, and all the heavier elements, mixes with the interstellar gas. And when that gas eventually collapses to form new stars and planets, those heavy elements are incorporated. Every atom of carbon in your body was created in a star. Every atom of oxygen, the iron in your blood, was forged in a stellar core and scattered by a supernova explosion. You are made of supernova remnants. The expanding shells we see, the beautiful, glowing nebulae like the Crab or the Vela, are the stuff of future planets. Future people, they re the raw materials for the next cycle of stellar and planetary evolution. Supernova remnants are not scars. They reseeds, places where the galaxy is enriched, where conditions are created for new star formation, where the cycle continues. The remnant expands, fades, disperses, but its contribution to the galaxy is permanent. The heavy elements it scattered will be here for the rest of time, cycling through stars and planets and life over and over. The supernova remnant is the star's gift to the future. Humans have been watching the sky for thousands of years, and occasionally they've seen supernovae. The 1054 supernova, visible for weeks in daylight, was recorded by Chinese astronomers and possibly by Native American observers. Chinese records describe a guest star that appeared in July 1054, remained visible for 653 days, and then faded. They noted its position, its brightness, its duration. Those records allowed modern astronomers to identify the Crab Nebula as the remnant. In 185 AD, Chinese astronomers recorded another guest star visible for 8 months. Modern analysis suggests this was a supernova, and we've tentatively identified its remnant, RCW86, a faint, expanding shell of gas. In 1572, Tycho Brahe's supernova appeared in Cassiopeia. Tycho observed it carefully, measured its position, noted that it showed no parallax, meaning it was far more distant than the moon or planets. This was revolutionary. Aristotelian philosophy held that the heavens beyond the moon were perfect and unchanging, but here was a new star, appearing and disappearing, proving that change occurred even in the supposedly eternal celestial sphere. Kepler's supernova in 1604 was the last visible in our galaxy. It appeared in Ophiuchus bright enough to be visible during the day. Kepler, a meticulous observer, recorded its brightness, position, and color changes as it faded. His observations helped us understand what we were looking at, though he, of course, had no idea what caused it. The word supernova wasn't coined until 1931. In 1987, a supernova appeared in the Large Magellanic Cloud, a small galaxy orbiting our Milky Way. It was visible to the naked eye from the southern hemisphere, the first naked-eye supernova since Kepler. Astronomers observed it with every available instrument. We learned more from that one supernova than from decades of studying distant ones. We saw the progenitor star in old photographs, a blue supergiant called Sanduleak, minus 69 degrees 202. We detected neutrinos from the core collapse, confirming theories about how supernovae work. Supernovae have always fascinated us. The sudden appearance of a bright new star, where none was before, the slow fading, the mystery of what it meant. Ancient astronomers often interpreted supernovae as omens, good or bad, depending on cultural context. A message from the gods, a sign of change. And in a sense, they were right. Supernovae do bring change. They scatter elements that will become part of new stars, new planets. They trigger star formation. They shape the evolution of galaxies. We've only recently, in the last century, come to understand what supernovae actually are. Exploding stars, core collapse, energy release beyond imagination. If anything, it is increased. Now we know that supernovae are not omens but processes. Natural, necessary, productive. They how the universe creates complexity, how dead stars give birth to new ones. The ancient observers were watching creation, even if they didn't know it. Let's talk about the sheer amount of energy a supernova releases. The numbers are almost incomprehensible, but they worth trying to grasp. A typical core collapse supernova releases about 10 circumflex, 46 joules of energy. Written out, that is 1 followed by 46 zeros. A number so large it is meaningless without context. Here is some context. The Sun releases about 40 fen 10 circumflex 26 joules per second. That is the solar luminosity, the total energy output of the Sun every second. A supernova releases about 10 circumflex 46 joules total. That is about as much energy as the Sun releases in 10 billion years. The Sun's entire main sequence lifetime worth of energy released in a few seconds. Another way to think about it, a supernova releases about 100 times more energy than the Sun will release during its entire existence, not per second, total. Everything the Sun will ever put out, times 100. In a few seconds, about 99% of the energy is carried away by neutrinos, tiny, nearly massless particles that barely interact with matter. They stream out of the collapsing core and pass through the star, through space, through planets, through you, without slowing down or interacting. When supernova 1987A exploded, neutrino detectors on Earth detected a burst of neutrinos, just a few dozen neutrinos, out of the unimaginable number that passed through Earth. But those few detections confirmed that our theories about supernova core collapse were correct. The neutrinos arrived about 3 hours before the light, because they escaped from the core immediately, while the light took hours to diffuse through the expanding gas. The remaining 1% of the energy, still an enormous amount, comes out as kinetic energy of the expanding gas and as light. That 1% is enough to power the visible explosion, to accelerate gas to thousands of miles per second, to shine brighter than a galaxy. The energy comes from gravitational collapse. When the core collapses from Earth, sized to city, sized, it releases gravitational potential energy, the energy stored in the separation of masses under gravity. This is the same kind of energy that heats you up when you fall and hit the ground, but on a cosmic scale. The core's gravitational binding energy is enormous. When that energy is released suddenly during the collapse, it has to go somewhere. Most of it goes into neutrinos. The rest goes into blowing the star apart. It is efficient. In a way, gravity compresses the core. The compression releases energy. The energy destroys the star. The destruction scatters elements across space. The elements form new stars. Those stars create gravity, which compresses cores, which the cycle continues. The energy of a supernova is terrifying and beautiful, enough to destroy a star, enough to enrich a galaxy, enough to trigger new star formation and seed future planets with the elements needed for life. Destruction on an unimaginable scale, but purposeful, productive, necessary. After the supernova explosion, after the outer layers have been blown into space, after the light has faded, something remains at the center. The core, the collapsed iron heart of the star, crushed by gravity into a ball about 12 miles across. This is a neutron star. Imagine all the mass of the Sun, or perhaps even more, 1.5 or 2 solar masses, compressed into a sphere the size of a city. Manhattan is about 12 miles long. You could fit a neutron star within the area of a large city. The density is incomprehensible. A teaspoon of neutron star material would weigh about 1 billion tons. A sugar, cube-sized piece would have more mass than all of humanity combined. How is this possible? Remember how white dwarfs are supported by electron degeneracy pressure. Neutron stars are similar, but taken to an extreme. When the core collapses, the electrons are crushed into the protons. Literally forced together by the immense pressure, electron plus proton becomes neutron. The entire core converts into a sea of neutrons, packed as tightly as they can possibly be. This is neutron degeneracy pressure. Like electron degeneracy, it is a quantum mechanical effect. Neutrons can't occupy the same quantum state. When they're compressed together, they resist further compression. And this resistance, this quantum mechanical refusal to be crushed further, is what holds the neutron star up against gravity. The surface of a neutron star is solid. Well, as close to solid as matter can be. It is a crust made of neutron, rich nuclei arranged in a crystalline lattice, one of the hardest substances in the universe. Beneath the crust is a superfluid of neutrons, neutrons flowing without friction, without viscosity, in a quantum state we can barely comprehend. And deeper still, in the core, the matter might be even stranger, quark matter perhaps, or exotic forms of matter that only exist under these extreme conditions. We don't know for sure. Our physics starts to break down at these densities and pressures, but what we do know is this: neutron stars are stable. Once formed, they don't collapse further, unless more mass is added. They just sit in space, incredibly dense, incredibly small, slowly cooling and spinning. And many of them spin very, very fast. When the core collapsed, it conserved angular momentum. Just like an ice skater, pulling in their arms spins faster. The collapsing core spun up. A star that was rotating once every few days before collapse might be rotating hundreds of times per second afterward. Neutron stars can spin faster than a kitchen blender. Hundreds of rotations per second, and they're 12 miles across and way more than the Sun. The physics involved, the stress on the crust, the centrifugal forces, the magnetic fields, is mind-bending. Neutron stars are relics of supernovae, the cores left behind when massive stars explode. They're small, dense, strange, and fascinating, and some of them do something even stranger. They pulse. In 1967, a graduate student named Jocelyn Bell Burnell was studying radio signals from space. She noticed something odd, a signal that pulsed regularly like a beacon. Once every 1.33 seconds, a burst of radio waves. At first, she and her advisor joked that it might be a signal from aliens. They nicknamed it LGM-1 for Little Green Men -1. But they quickly realized it was natural, and within a few months, they found more pulsing sources. These objects were named pulsars. We now know that pulsars are rapidly spinning neutron stars with strong magnetic fields. Here is how they work. A neutron star has a magnetic field, sometimes billions of times stronger than Earth. This field isn't T-aligned with the star's rotation axis. It is tilted, like Earth's magnetic field is tilted relative to the rotation axis, and the magnetic field channels radiation into beams that emerge from the magnetic poles. As the neutron star spins, these beams sweep through space like lighthouse beams. If Earth happens to be in the path of one of these beams, we see a pulse of radiation every time the beam sweeps past us. Pulse, 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 perfectly regular, timed by the neutron star's rotation. The fastest known pulsar spins 716 times per second, 716 rotations. An object with more mass than the Sun, 12 miles across, spinning so fast that a point on its equator is moving at about 1/10 the speed of light, and the pulses are incredibly regular. Some pulsars keep better time than atomic clocks. We can predict when the next pulse will arrive to within microseconds. But pulsars do slow down. Very slowly. They re-losing rotational energy, mostly through magnetic braking. The magnetic field interacts with charged particles in the surrounding space, transferring energy and slowing the rotation. A typical pulsar might slow by about 1 second per million years. That sounds like nothing, and it is nothing, practically. But it is measurable. We can track pulsars over decades and watch them slow down. And as they slow, they eventually stop being visible as pulsars. The rotation slows enough that the beams weaken, or the beam no longer sweeps past Earth, or the mechanism that creates the radio emission shuts down. Old neutron stars, billions of years old, are no longer pulsars. They re-still spinning, but too slowly and too weakly to produce the beams we detect. They re-just dark, dense, slowly cooling relics drifting through space. But young pulsars, especially those in supernova remnants, still surrounded by the gas from the explosion, are bright and active. They pulse rapidly, powerfully, lighting up the remnants around them. The pulsar in the Crab Nebula spins 30 times per second. It powers the entire nebula's glow, pumping energy into the expanding gas, keeping it lit thousands of years after the explosion. Pulsars are cosmic lighthouses, beacons sweeping through space, marking the locations of neutron stars, providing precise clocks we can use to study gravity, space, and time. They re-strange, beautiful, utterly alien, and they re the slowly cooling remnants of stars that died violently. Some neutron stars have magnetic fields even stronger than normal, incredibly, almost impossibly strong. These are called magnetars. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth. That is already incomprehensibly powerful, but a magnetar's field is 1,000 times stronger still, 1 quadrillion times Earth's field. At this field strength, strange things happen. Atoms are distorted. The electron clouds around nuclei stretch into elongated shapes, no longer spherical. Chemistry as we know it does. Quantum electrodynamics, the physics of light and matter, behaves differently. If you brought a piece of regular matter near a magnetar, the magnetic field would rip the electrons away from the atoms. The matter would disintegrate into a plasma of ions and electrons. And if you somehow approached a magnetar, which you can because you'd be dead long before you got close, the magnetic field would affect the bioelectric signals in your nervous system. Your neurons fire, using electrical impulses. A magnetar's field would disrupt those impulses completely. You wouldn't just die. You cease to function on a cellular level. But magnetars aren't just strong, they reactive. The magnetic field is so intense that it stresses the neutron star's crust. Think of the crust as a solid shell under incredible magnetic tension. Sometimes that tension becomes too great. The crust cracks. And when it does, the magnetic field reconfigures violently, releasing enormous amounts of energy. This is called a magnetar flare. In a fraction of a second, a magnetar can release more energy than the sun emits in a year. The energy comes out as gamma rays and X-rays, the most energetic forms of light. If a magnetar flared within a few light years of Earth, the radiation could damage our ozone layer, disrupt satellites, cause extinctions. Fortunately, the nearest known magnetar is thousands of light years away. In 2004, a magnetar called SGR 1806-20, located about 50,000 light years away, produced the largest flare ever recorded. The burst of energy was so intense that it affected Earth's ionosphere. From 50,000 light years away, a neutron star briefly disrupted our planet's atmosphere. The energy involved is almost unimaginable, and it all comes from the magnetic field. The field contains so much energy that when it shifts, when the crust cracks and the field lines snap and reconnect, the release is cataclysmic. Magnetars eventually calm down. Over thousands of years, the magnetic field decays. The crust stabilizes. The flares become less frequent, less energetic, and eventually the magnetar becomes an ordinary neutron star, still dense, still spinning, but no longer actively magnetic. But while they re-young, magnetars are among the most violent objects in the universe. Not violently moving, they just sit in space spinning, but violently erupting, releasing more energy in seconds than entire stars release in years. They rare. We've only discovered a few dozen, but they out there, scattered through the galaxy, occasionally flaring, reminding us that even dead stars can be dangerous. Magnetars are proof that the universe's extremes go beyond what we can easily imagine, that nature finds ways to concentrate energy and matter to levels that seem impossible. If you convert pulsar radio signals into sound waves, speeding them up or slowing them down to frequencies humans can hear, pulsars sound like they ticking, tick, tick, perfectly regular, like a metronome, like a cosmic clock, keeping time in the darkness. Some pulsars tick slowly once per second, once every few seconds, a slow, patient rhythm. Others tick rapidly, multiple times per second, a quick, urgent drumming. The fastest pulsars sound like a buzz or a hum when converted to audio, rotating so fast that the individual pulses blur together into a continuous tone. Radio astronomers have created audio versions of pulsar signals, and they eerie, beautiful. Not the kind of sound you'd expect from space. Space is silent after all, no medium for sound waves to travel through. But the radio signals, when converted, create something that feels almost musical. Each pulsar has its own signature, its own period, its own drift rate as it slows down. You could, in theory, identify a pulsar just by listening to its tick. And some pulsars have companions, binary pulsars, neutron stars orbiting other stars, show periodic variations in their pulse timing as they orbit. The pulses arrive slightly earlier when the pulsar is moving toward us, slightly later when moving away. A Doppler shift in time, creating a rhythm that speeds up and slows down in a cycle. In 1974, astronomers discovered a binary pulsar system where both stars are pulsars. PSR B 1913 plus 16. Two neutron stars orbiting each other, both pulsing, both slowing down, and the orbit itself is shrinking as the system radiates gravitational waves, ripples in spacetime, predicted by Einstein. By timing the pulses from this system precisely, astronomers confirmed that gravitational waves exist decades before we directly detected them with LIGO. The pulsars were clocks, and by watching how their ticking changed, we could see spacetime itself rippling. Pulsars are nature's timekeepers. Some of them are more stable than our best atomic clocks. We can use them to test theories of gravity, to navigate spacecraft, to study the interstellar medium. And the sound, the tick, 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 is oddly comforting. It is regularity in a chaotic universe. It is proof that even in the aftermath of violence, even after a star has exploded and left behind a crushed core, there can still be rhythm, pattern, predictability. The pulsars tick in the dark. No one hears them directly. Radio telescopes detect the signals and convert them to data, to graphs, to audio files that scientists listen to. But the ticking continues whether we listen or not. Hundreds of pulsars throughout the galaxy, all ticking at different rates, all slowing imperceptibly, all marking time in the void. It is like the universe has a heartbeat. Not one heartbeat, but many. Each pulsar a heart, still beating long after the star that made it has died. Tick, tick, the sound of dead stars, still keeping time. Sometimes two neutron stars orbit each other, binary systems, locked in gravitational embrace, spiraling slowly inward as they radiate gravitational waves. Over millions or billions of years, the orbit shrinks. The neutron stars get closer, and eventually, inevitably, they collide. The merger of two neutron stars is one of the most energetic events in the universe, second only to supernovae. When they collide, the gravitational waves released ripple through space-time across the entire universe. LIGO and Virgo, gravitational wave detectors on Earth, have detected several neutron star mergers. The signal is distinctive, a rising pitch, a chirp, as the stars spiral faster and faster until they merge. And the merger produces light. Lots of light. When neutron stars collide, they heat to billions of degrees. They eject material, neutron, Rich matter flung into space at high speeds, and in this ejected material, rapid neutron capture happens. Free neutrons are absorbed by atomic nuclei, creating heavier and heavier elements. This is how gold is made: platinum, uranium, all the elements heavier than iron that can be produced in normal supernovae. They, remade in neutron star mergers, the ejected material glows with what is called a kilonova. It is similar to a supernova, but powered by radioactive decay of the heavy elements being created. The glow lasts for days or weeks, and it is enriched with gold, platinum, and other rare elements. Every gold atom on Earth in jewelry and electronics, in your body, was created in a neutron star merger billions of years ago, before the solar system formed. The gold was scattered into space, mixed with gas and dust, incorporated into the cloud that collapsed to form the sun and planets. When you wear gold, you are wearing neutron star collision debris. In 2017, astronomers detected a neutron star merger with both gravitational waves and light, GW170817. The gravitational wave signal arrived first, followed seconds later by a gamma-ray burst, then hours later by the kilonova glow. Telescopes around the world observed the afterglow. They watched it brighten and fade. They analyzed the spectrum and confirmed. Yes, heavy elements, gold, platinum, uranium, all being created in real time as the ejected material decayed. It was the first time we'd seen both gravitational waves and light from the same event. A multi-messenger observation that confirmed decades of theory about how heavy elements are made. And it showed that the universe is still working, still creating, still forging elements and scattering them across space. The process that created the gold on Earth is still happening. In distant galaxies, whenever neutron stars collide, the collisions are rare. In a given galaxy, they might happen once every 100,000 years, but there are billions of galaxies. The universe is large. Somewhere right now, neutron stars are colliding somewhere, gold is being made, and billions of years from now, that gold might be part of a planet, might be mined by life that doesn't exist yet. Might become a ring or a circuit or a part of someone's body. The cycle continues. Death creates. Collisions produce. The universe builds complexity from violence. Not all neutron stars remain neutron stars forever. Some, if they accrete matter from a companion, or if they merge with another neutron star, gain enough mass that neutron degeneracy pressure can no longer hold them up. There is a limit, just like the Chandrasekhar limit for white dwarfs. The Tolman, Oppenheimer, Volkoff limit, usually just called the Tove limit, is about 2 to 3 solar masses. If a neutron star exceeds this mass, neutron degeneracy fails, and the neutron star collapses. But into what? There is nothing below neutron degeneracy to stop the collapse. No next level of quantum pressure, just gravity, pulling inward, crushing matter to infinite density. The neutron star collapses to a point, a singularity, a place where density becomes infinite and space-time curvature becomes infinite. And around that singularity, space-time is so warped that nothing, not matter, not light, not information, can escape. This is a black hole. The collapse happens quickly. A neutron star that exceeds the Tove limit collapses in a fraction of a second. And from the outside, you see nothing. The neutron star would dim. Its light would redshift, stretching to longer and longer wavelengths as gravity grew stronger. And then it would wink out, disappear. The light that was emitted just before the collapse would be trapped, unable to escape the intensifying gravitational pull. All that would remain is gravity. The black hole's gravitational field, pulling on everything around it just like the neutron star. But now with an event horizon, a boundary beyond which escape is impossible. The event horizon is not a physical surface. It is a mathematical boundary in space-time, the point of no return. Cross the event horizon going inward, and you cannot come back out. The geometry of space-time inside the horizon is such that all paths lead inward toward the singularity. Trying to escape a black hole from inside the event horizon is like trying to travel backward in time. The structure of space-time 1, 2 allow it. For a black hole with the mass of the Sun, the event horizon would be about 3 kilometers in radius. For a black hole with 10 solar masses, typical for a black hole formed from a collapsing neutron star. The event horizon would be about 30 kilometers in radius, tiny, much smaller than the original star, even smaller than the neutron star that preceded it. All that mass compressed so tightly that it warps space-time into a trap, and inside, we don't know. Our physics breaks down at the singularity. General relativity predicts infinite density and infinite curvature, but infinite usually means our equations don't work anymore. Quantum gravity, a theory we don't yet have, would be needed to describe what is really happening at the center of a black hole, but from the outside, it doesn't matter. The black hole exists, it has mass, it has gravity, it warps space-time, and it traps light. The final collapse, the ultimate death, a star crushed to a point, surrounded by a horizon of no return. The event horizon is the defining feature of a black hole. It is the boundary that separates can escape from cannot escape. Outside the event horizon, light can escape. It is redshifted by the black hole's gravity, stretched to longer wavelengths, carrying less energy, but it can escape. A spaceship outside the event horizon, with powerful enough engines, could accelerate away from the black hole and escape to safety. But inside the event horizon, escape is impossible, not difficult, not requiring impossible amounts of energy. Actually, fundamentally impossible. The structure of space-time is such that all future directed paths lead inward. There is no path outward. Trying to escape would be like trying to reach yesterday, a direction that doesn't exist. The event horizon size depends on the black hole's mass. The relationship is simple. The Schwarzschild radius is about 3 kilometers per solar mass. A 10 solar mass black hole has an event horizon at 30 kilometers. A 1,000,000 solar mass black hole has an event horizon at about 3 million kilometers, roughly 4 times the radius of the Sun. Crossing the event horizon is, theoretically, not dramatic. If you fell into a large black hole, a supermassive one with millions or billions of solar masses, you wouldn't even notice crossing the horizon. There is no physical barrier, no wall, no sensation. Space-time is smoothly curved, and you cross the horizon just by falling through space. But you would notice the tidal forces. Gravity gets stronger as you get closer to the black hole's center. If you're falling feet first, your feet are closer to the center than your head, so they experience stronger gravity. This creates a tidal force, a stretching. For a small black hole, this tidal stretching becomes extreme near the event horizon. You'd be torn apart by the difference in gravitational pull between your feet and head, spaghettified, as physicists cheerfully call it, stretched into a long, thin strand of atoms before you even reach the horizon. But for a large black hole, the tidal forces at the event horizon are gentle. You'd cross the horizon intact, still alive, still experiencing normal space around you, and then, after crossing, you'd have a finite amount of time, possibly hours, for a supermassive black hole before you reach the singularity. And during that time, you could look out. You'd see the universe outside, but bluer and faster. Light from the external universe would be blue-shifted as it falls in with you, and time outside would appear to pass faster, but you could never send a signal out. Anything you emit, light, radio waves, particles, falls inward with you. The event horizon is one way. From the outside, however, you never quite cross. Due to gravitational time dilation, clocks near the horizon run slow compared to clocks far away. To an outside observer, you'd appear to slow down, freeze, and fade as you approach the horizon, never quite crossing. Both perspectives are correct. You cross in your own reference frame. You never cross in the outside reference frame. Relativity allows both. The event horizon is a boundary in space-time, and boundaries, even intangible ones, have power. Black holes accumulate. Everything that falls in, matter, light, information stays in, forever. A black hole that forms from a collapsed neutron star starts with about 10 solar masses. If it is alone in space, far from any source of matter, it will remain 10 solar masses, essentially, forever. It will slowly evaporate through Hawking radiation, a quantum mechanical process that we'll discuss, but that takes longer than the current age of the universe. But if the black hole is in a rich environment, near a companion star, in a dense star cluster, at the center of a galaxy, it can grow. Gas falls in, dust falls in. Stars that wander too close get torn apart by tidal forces, and their shredded remains spiral inward. As matter falls toward a black hole, it doesn't drop straight in. It has angular momentum. It is moving sideways as well as inward. So it spirals. And as it spirals, it forms an accretion disk, a swirling disk of gas and dust, heated by friction and compression, glowing brightly. The accretion disk can be hotter and brighter than the black hole's original star was. Gas in the inner regions of the disk is heated to millions of degrees, hot enough to emit X-rays. So black holes, ironically, can be some of the brightest objects in the universe. Not because the black hole itself emits light, it doesn't, by definition, but because the accretion disk around it glows with the energy of infalling matter. We detect black holes by their accretion disks, by the X-rays emitted as matter spirals inward, by the way stars orbit invisible companions, their motion revealing the presence of a dark, massive object. And once matter crosses the event horizon, it is gone, irretrievable. It adds to the black hole's mass, makes the event horizon slightly larger, but the matter itself is lost to the outside universe. This creates a puzzle. Information is supposed to be conserved in quantum mechanics. If you know the exact state of a system now, you can calculate what it was in the past and what it will be in the future. Information doesn't disappear. But in a black hole, it seems to matter falls in, carrying information about its quantum state. And that information crosses the horizon, goes to the singularity. And then what? Is it destroyed? Is it encoded somehow in the black hole's properties? Is it radiated back out in Hawking radiation, in scrambled form? This is the black hole information paradox, and it is not fully solved. Physicists have proposed various solutions, but we don't have a definitive answer. But from a practical standpoint, it doesn't matter much. What falls in doesn't come out. Whether the information is truly lost or cleverly preserved in a way we don't understand yet, the effect is the same. The matter is gone from the observable universe. The black hole grows, slowly, steadily, consuming whatever falls within reach. It is not actively sucking things in. Gravity doesn't work that way, but anything that crosses the event horizon is claimed forever, a one-way accumulator, growing larger over time, patient and inexorable. In 1974, Stephen Hawking made a startling discovery. He showed that black holes aren't completely black. They emit radiation, very slowly, very faintly, but they emit. This is Hawking radiation, and it comes from quantum effects near the event horizon. Here is the idea in quantum mechanics. Empty space isn't truly empty. It is filled with quantum fluctuations, virtual particles that pop into existence in antiparticle pairs, exist briefly, and then annihilate each other. Normally, these fluctuations have no observable effect. They appear and disappear too quickly to matter. But near a black hole's event horizon, something different can happen. A particle-antiparticle pair can form right at the horizon. One particle falls into the black hole, the other escapes. From far away, it looks like the black hole emitted a particle. The black hole loses energy in this process. The infalling particle has negative energy relative to infinity, and it reduces the black hole's mass slightly. The escaping particle carries positive energy away, so the black hole radiates. It emits particles. It loses mass. This process is incredibly slow. For a stellar, mass black hole, 10 solar masses or so, the Hawking radiation is undetectably faint. The temperature of the radiation is about a billionth of a Kelvin. That is colder than the cosmic microwave background, the radiation left over from the Big Bang. So the black hole actually absorbs more energy from the cosmic microwave background than it emits via Hawking radiation. It is gaining mass, not losing it. But in the far future, after the cosmic microwave background has cooled through the expansion of the universe, after all the stars have burned out, after the universe is dark and cold, Hawking radiation will dominate, and the black hole will evaporate, very, very slowly. A 10 solar mass black hole will take about 10 circumflex 67 years to evaporate completely. That is one followed by 67 zeros. Far, far longer than the current age of the universe. But smaller black holes evaporate faster. The evaporation time goes inversely with mass. A black hole with the mass of a mountain would evaporate in about a second, releasing as much energy as a nuclear bomb. As a black hole evaporates, it gets smaller, and as it gets smaller, its temperature increases. The final stages of evaporation happen quickly. The last few moments of a black hole's life are a burst of radiation, a final flash before it disappears entirely. Theoretically, anyway. We've never seen this. The universe isn't old enough for any black holes to have evaporated yet. But if Hawking's calculation is correct, and most physicists believe it is, then black holes are temporary. Given enough time, they evaporate into radiation. Even black holes die. Eventually, on timescales so long that they make stellar lifetimes look like eye blinks, but they die. Nothing is truly eternal. Not stars, not white dwarfs, not neutron stars, not even black holes. Everything in the universe is temporary, just on different timescales. At the centers of most galaxies, including our own Milky Way, there is a supermassive black hole. These aren't formed from collapsing stars. They are millions or billions of times more massive than the Sun, far too large to have come from any single star. How they form is still debated. Maybe they grew from smaller black holes that merged. Maybe they formed directly in the early universe from collapsing gas clouds. Maybe they started as large black holes and grew by accreting matter over billions of years. Whatever their origin, they re there. At the center of the Milky Way is Sagittarius A, pronounced Sagittarius A star, a black hole with about 4 million solar masses. It is about 26,000 light years from Earth, sitting at the galactic center, surrounded by stars, orbiting it at incredible speeds. We've tracked these stars, designated S2, S62, and so on, orbiting the black hole. S2 has an orbital period of about 16 years. At its closest approach, it is moving at almost 3% the speed of light. By watching its orbit, we can measure the black hole's mass precisely. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together, produced the first image of a black hole, Event Horizon. Not Sagittarius A, but the supermassive black hole at the center of the galaxy M87, about 55 million light years away. The image showed a bright ring of emission surrounding a dark center. The dark center is the black hole's shadow, the region from which no light can escape. The bright ring is the accretion disk, glowing as matter spirals inward. It is a remarkable image, proof that black holes are real, that event horizons exist, that general relativity's predictions hold even in these extreme conditions. Supermassive black holes can power quasars, incredibly luminous objects visible across the universe. When a supermassive black hole is actively accreting matter, the accretion disk can outshine the entire galaxy. Quasars are the brightest sustained objects in the universe, powered by black holes consuming stars and gas. But our galactic center black hole is quiet. It is not actively accreting much matter, just occasionally pulling in a gas cloud or a star that wanders too close. It is dormant, relatively speaking. Still, it is there, a 4 million solar mass black hole sitting at the center of our galaxy, around which 200 billion stars orbit over hundreds of millions of years. And someday, billions of years from now, when the Milky Way and Andromeda galaxies collide and merge, the two supermassive black holes at their centers will spiral together and merge. The resulting black hole will be even larger, and the collision will release gravitational waves powerful enough to ripple across the universe. Black holes, even supermassive ones, are part of the cosmic cycle. They grow, they merge, they shape galaxies, they power quasars, and eventually, on timescales beyond imagining, they evaporate. Even the largest black holes are temporary, just very, very long-lived temporary. Let's bring this home. Let's talk about our sun, our star, the one that warms Earth, powers photosynthesis, makes life possible. It has been shining for 4.6 billion years. It is halfway through its main sequence lifetime. In about 5 billion years, it will run out of hydrogen in its core, and then it will begin to die. The process will be slow, gradual, following the same stages we've discussed: red giant, helium flash, planetary nebula, white dwarf. First, the The core will contract. Helium will accumulate. The hydrogen shell around the core will begin fusing more vigorously. The sun will brighten. Over hundreds of millions of years, it will become perhaps 10% brighter than it is now. This will be bad for Earth. Even a 10% increase in solar output will raise Earth's temperature significantly. The oceans will evaporate faster. The atmosphere will become more humid. The greenhouse effect will intensify. Eventually, probably within the next billion years or so, Earth will become uninhabitable. The oceans will boil away. The atmosphere will be steamed off into space. The surface will become a scorched, airless desert. This is Earth's fate, even before the sun becomes a red giant, just from the gradual brightening as the sun ages. And then, about 5 billion years from now, the sun will leave the main sequence. The core will run out of hydrogen. The sun will begin to expand. Over the next few 100 million years, it will swell into a red giant. It will grow to perhaps 100 times its current diameter, large enough to engulf Mercury, large enough to engulf Venus, large enough to reach, or nearly reach, Earth's east current orbit. By this time, Earth's orbit will probably have drifted outward slightly. The sun, as it loses mass through stellar winds, will have weaker gravity. Earth will spiral outward. It might avoid being swallowed, but it doesn't matter. Earth will already be a lifeless, molten rock. The heat from the red giant sun will vaporize any remaining atmosphere. The surface will melt. Earth will be a ball of magma, orbiting a dying star. Mars will warm up for a brief period. Maybe a few 100 million years, Mars might be warm enough for liquid water, but it is too late for life to evolve there. The Sun's red giant phase 1 last long enough. The outer planets, Jupiter, Saturn, Uranus, Neptune, will receive more heat. Their atmospheres will change. Their moons might warm, but again, it is temporary. And then the sun will expel its outer layers in a planetary nebula. The glowing shell of gas will expand past the planets, scattering the sun's material into space. What remains will be the core, a white dwarf about the size of Earth, slowly cooling. The solar system will be dim, cold. The white dwarf will provide some light, but not much. The planets will orbit a fading ember. This is our sun's future, inevitable, distant, but certain. When the sun becomes a red giant, the inner planets will die. Mercury, Venus, possibly Earth consumed or scorched. Their atmospheres stripped away, their surfaces melted, their stories ended, but they won't disappear entirely. Even if they're swallowed by the sun's expanding atmosphere, they won't vaporize completely. They'll spiral inward, losing mass. But their cores, the dense metallic centers, might survive. They'd orbit inside the red giant's outer layers, slowly being eroded, eventually falling into the sun's core. Or, if they avoid being swallowed, they'll remain in orbit as dead, lifeless rocks. No water, no air, just bare stone and metal, baked sterile by the red giant's heat. It is farther out, it won't be consumed, and for a brief time, it might be warm and wet. But as the sun loses mass and the planets drift outward, Mars will cool again. And when the sun becomes a white dwarf, Mars will freeze permanently. The outer planets, Jupiter, Saturn, Uranus, Neptune, will survive largely intact. Their orbits will shift outward as the sun loses mass. Their atmospheres will change in response to the varying solar radiation. But they're mostly hydrogen and helium. They don't have surfaces to melt or atmospheres to strip in the way rocky planets do. The moons of the outer planets might be interesting. Europa, Enceladus, Titan, moons with subsurface oceans or thick atmospheres, might become more active as they warm up. But again, it is temporary. And then the planetary nebula phase. The sun's outer layers expand outward, passing the planets. For a few thousand years, the planets will be inside a glowing shell of gas. And then the gas will disperse, leaving the planets in orbit around a white dwarf. The solar system will be dark. The white dwarf will shine but dimly far less light than the sun provides now. The planets will be cold. Jupiter and Saturn might provide some light from the heat they radiate. But it won't be much. Over billions of years, the white dwarf will cool. The planets will cool. The solar system will become a cold, dead system, orbiting a dark ember. Eventually, trillions of years in the future, the planets might drift away. Gravitational interactions with passing stars could eject them from the solar system, or they might collide with each other, or they might be captured by other stars, or they might just remain in orbit forever, frozen and dead, around a black dwarf that was once the Sun. The planet's fate is tied to the Sun's. When the Sun dies, the solar system dies with it, not immediately, not all at once, but eventually. The planets will outlast the Sun's light, but they won't outlast time. Nothing does. And billions of years from now, if some interstellar traveler passes through this region of space, they might find a few cold, dark planets orbiting a cold, dark star and wonder what stories they could tell. Will life on Earth survive the Sun? Death? Number not on Earth. Earth will become uninhabitable long before the Sun becomes a red giant. But will life, Earth origin life, descendants of bacteria and plants and animals that exist now, will it survive somewhere else? Maybe, if humanity survives the next few billion years, a staggeringly long time, far beyond any reasonable prediction, it could spread to other star systems, colonize planets around younger stars, stars that will still be on the main sequence when the Sun dies. And if life spreads that way, then yes, Earth, origin life, will survive the Sun's death. Just not on Earth, somewhere else. In some other solar system, carried there by descendants we can imagine. Using technology we can conceive. Or maybe life will move to the outer solar system. As the Sun brightens and Earth becomes uninhabitable, the outer planets and their moons will warm. For a brief window, geologically speaking, Europa or Enceladus or Titan might be habitable. Life could migrate outward, move to new homes as the old ones become uninhabitable, hopping from planet to moon, following the habitable zone as it shifts outward with the dying Sun. But eventually, the Sun will run out of fuel, the habitable zone will disappear, and life will have to leave the solar system or die. More likely, though, life will die long before the Sun does. Not from the Sun, but from other causes. Asteroid impacts, climate change, human-caused catastrophes, natural disasters. Evolution might take us in directions we can't predict, might replace us with something else. A billion years is a very long time. Most species don't last a million years. Humanity, Homo sapiens, has existed for maybe 300,000 years. What will we be in a billion years? Still recognizably human. Evolved into something else, extinct, we can know, but the possibility exists. The slim, beautiful possibility that life from Earth might outlast Earth itself, that the bacteria and plants and animals and humans and whatever comes after might spread across the galaxy, adapting to new worlds, diversifying into forms we can imagine. And billions of years from now, when the Sun becomes a red giant and Earth is a scorched rock, maybe there will be beings somewhere in the galaxy who remember that Earth is where their ancestors came from, who know that the Sun is dying and who mourn it gently from a safe distance. Or maybe not. Maybe life is fragile. Maybe Earth is the only place it ever flourished. Maybe we'll be alone until the end. Either way, the Sun will die. Earth will die. The solar system will grow dark and cold. But the atoms that made Earth will still be here, scattered by the planetary nebula, mixed with the interstellar medium, ready to become part of new stars, new planets, maybe new life. The cycle continues. Always. Whether life persists or not, the universe keeps creating. After the Sun sheds its outer layers, after the planetary nebula fades and disperses, what remains is the core, a white dwarf, about the size of Earth, made of carbon and oxygen, incredibly dense, hot, over 100,000 Kelvin initially, but no longer fusing. The white dwarf Sun will shine. Not brightly, not like the Sun does now, but it will emit light. At first it will glow blue-white. Over millions of years, it will cool and dim, shifting from blue to white to orange to red. The planets, whatever remains of them, will orbit this white dwarf. They'll receive a little light, a little heat, but not much, not nearly enough to warm them. Earth, if it still exists, will be frozen. The oceans are long gone, boiled away when the Sun was a red giant. The atmosphere is gone. The surface is cold, dark, airless. a dead planet orbiting a dying star. But the white dwarf will last. For billions, even trillions of years, it will continue to radiate its stored heat into space, slowly cooling, slowly fading. In 10 billion years, it might be a red dwarf, a dim red glow, barely visible. In 100 billion years, it might be barely glowing at all. In a trillion years, it will be cold, a black dwarf, dark and silent. And the planets will still be there, orbiting, frozen, lifeless, but still there. The solar system will become a ghost, a relic of what it once was. The sun, which once powered photosynthesis and warmed oceans and supported life, will be a cold lump of carbon and oxygen. The planets, which once had weather and seasons and atmospheres, will be frozen wastelands. But they'll persist. For trillions of years, the solar system will exist in this dead state, not destroyed, not scattered, just cold and dark and still. Eventually, given enough time, the planets might drift away. The solar system could be broken up by the slow chaos of galactic dynamics. Or maybe the sun and its planets will orbit the galactic center forever, slowly cooling, slowly drifting, a dead system among billions of dead systems in a galaxy that itself is dying. But even in death, the solar system will exist. The atoms are still there, the mass is still there, gravity is still there. The sun will have gone from a bright life, giving star to a fading ember to a cold, dark crystal. But it will still be the sun, in some sense. Still, the same atoms, rearranged, cooled, quieted. And maybe that is okay. Maybe after 10 billion years of shining, the sun will have earned its rest, earned the right to cool and fade and sleep. The sun will die, but it will do so having given everything it could, having shone for billions of years, having made life possible, even briefly, on at least one planet. That is not a small thing, that is a life well lived, by any measure. When the sun is a cold, dark black dwarf, will anyone remember what it was? Will there be anyone left to remember that this cold lump of carbon once shone, that it once had planets with oceans and life, that it once warmed faces and powered photosynthesis and made shadows on summer afternoons? Maybe, if life spread to other stars, if some record was kept, if our descendants, billions of years removed, still tell stories about Sol, the sun, the star where it all began. Or maybe not. Maybe by then, the sun will be forgotten. If feelings dawn to have feelings, dawn to have pride or regret, the sun will just exist in whatever state it is in, doing what physics demands. Still, there is something poignant about the idea that a star could shine for 10 billion years, support life, make warmth and light, and then fade into darkness, forgotten. It makes you want to remember, to pay attention, to appreciate the sun while it is still shining. Every sunset, every warm day, every beam of light that touches your face, they all temporary, not just for you, not just for humanity, but for the sun itself. The sun is middle, aged. It has been shining for 4.6 billion years. It will shine for another 5 billion we alive during its prime, during the time when it is stable, reliable. And that is a gift, a temporary gift like all gifts, but a gift nonetheless. So maybe remembering the sun isn't about ensuring that someone in the far future knows its name. Maybe it is about recognizing, now, that it is shining, that it is giving, that it is here. Every photon that reaches Earth took 8 minutes to travel from the sun. But it took hundreds of thousands of years to work its way from the core, where it was created in fusion, up through the layers of the sun, scattering and being absorbed and re-emitted countless times, before finally reaching the surface and streaming toward Earth. The light touching you now began its journey in the sun's core, long before you were born, before civilization, before human. The photons are ancient travelers, finally reaching their destination, and the sun creates billions upon billions of them every second and has for billions of years. The sun is generous, profligate with its light, and it will continue to be until the fuel runs out. So remember the sun, not in the future, when it is a white dwarf or a black dwarf. Now, while it is shining, while it is warm, While it is giving everything it has to the solar system, to Earth, to life, the sun will die. But it is alive now, and that is what matters. Not the ending, but the shining. The sun is still shining, and you are here to see it. The universe is currently in what is called the stelliferous era, the time when stars shine. It is the age of stars, of galaxies, of light. But this era won't last forever. Star formation requires gas. Hydrogen gas, mostly. Stars form when clouds of hydrogen collapse under their own gravity, heat up, and begin fusing, but the supply of hydrogen is finite. And every star that forms uses up some of that hydrogen, fusing it into helium and heavier elements. Right now, stars are still forming. Not as rapidly as in the early universe. The peak of star formation was about 10 billion years ago. But they still forming. In our galaxy, perhaps one new star per year. But over time, the rate will decrease, less and less gas available. More and more gas locked up in dead stars, white dwarfs, neutron stars, black holes. That don't return it to the interstellar medium. Within the next few trillion years, star formation will essentially stop. The last stars will form. The galaxy will gradually darken as the massive bright stars die and are not replaced. Eventually, perhaps 100 trillion years from now, the last stars will burn out. The universe will consist of white dwarfs, neutron stars, black holes, and brown dwarfs, objects too small to fuse hydrogen. This is the end of the stelliferous era. The lights go out. The age of stars ends. But the universe continues. It is just dark now, cold, starless. White dwarfs cool into black dwarfs. Neutron stars cool, brown dwarfs cool. Everything radiates away its heat into the expanding void, slowly approaching absolute zero. After perhaps 10 circumflex 40 years, even the black dwarfs might begin to disintegrate through quantum processes. Proton decay, if it occurs, would slowly dissolve white dwarfs and the remnants of stars. And black holes evaporate. Slowly through Hawking radiation, they lose mass and eventually disappear in a final flash of radiation. The smallest black holes evaporate first. Stellar, mass black holes take 10 circumflex 67 years. Supermassive black holes take 10 circumflex 100 years or more. But given enough time, they all evaporate. All the black holes, all the mass that fell into them, radiated away into low-energy photons, spreading through the ever-expanding universe. Eventually, after timescales that make stellar lifetimes look instantaneous, the universe consists of nothing but low-energy photons, a few stray electrons and positrons, maybe some neutrinos, all spreading out in an ever colder, ever darker void. This is heat death, the final state. Maximum entropy. No structure, no stars, no galaxies, no life. Just a dilute gas of particles at nearly absolute zero, spreading forever. It is not violent, not catastrophic, just the slow, inevitable thermodynamic running down of everything. The stars die, the galaxies fade, the universe grows cold and dark and still, and there is a kind of peace in that, after all the activity, all the fusion and explosions, and life and death and creation. Eventually there is rest. The universe, having exhausted all its possibilities, settles into stillness, permanent, eternal, quiet. Let us put this in perspective. The universe is currently 13.8 billion years old. That is the time from the Big Bang to now. 13.8 billion years feels like a long time. It is a long time, but compared to the future, it is nothing. A brief flicker at the beginning. The last stars will burn out in about 100 trillion years. That is about 10,000 times the current age of the universe. We in the first 0.01% of the stelliferous era. We at the very beginning. And after the stelliferous era ends, the universe will continue for, well, essentially forever, depending on how you define forever. Black hole evaporation timescales stretch to 10 circumflex 100 years. That is a 1 followed by 100 zeros. If you tried to write out that number, it would have more digits than there are atoms in the observable universe. These timescales are so long that they're not just hard to imagine, they're functionally impossible to imagine. Your brain can hold numbers that large, they abstract, meaningless, except as concepts, but they real. The universe will exist for that long, empty, dark, cold, but existing. And here is the strange thing. We re-alive during the interesting part. The brief, bright period when stars shine and galaxies glow, and life is possible. After us, after all life, after all stars, there will be trillions upon trillions of years of darkness, an eternity of cold and silence. We re-witnessing the universe, in its youth, its energetic phase, the time when things happen, when structure forms, when light exists. It 1T last. Compared to the universe's total lifespan, the stelliferous era is a brief flash. The stars will shine for a while, and then they'll fade and the darkness will last forever. But that makes the stars more precious, doesn't it? More valuable. They re-temporary. Rare even in the full span of the universe's existence. Stars exist only in the first tiny fraction of time. We incredibly lucky to be alive when the universe is bright. When there are stars to see, galaxies to observe, light to warm us. In the far future, if something conscious exists, which it almost certainly won't, but if it did, it would be in a dark universe. No stars, no galaxies, just cold remnants drifting through infinite space. They never know what stars were, never see light from distant sources, never experience a sunrise. But we do. We get to see the stars. We get to witness the universe while it is still alive, still creating, still shining. And that is a privilege. A temporary privilege, like everything in the universe, but a real one. The universe will be dark far longer than it will be bright. But right now, it is bright. And we here to see it. The stars are shining, and that is enough. Someday there will be a last star. The final star to form from the last available gas. The youngest star, the one that will outlive all others. It will be a red dwarf. Almost certainly. Red dwarfs are the most common stars and the longest lived. The smallest ones can shine for 10 trillion years or more, and this final red dwarf will shine alone. All the other stars, the massive ones, the medium ones, even the other red dwarfs that formed earlier, will have died already. Galaxies will have collided and merged. Star formation will have stopped everywhere. The universe will be mostly dark, filled with white dwarfs and neutron stars and black holes. And in one galaxy, somewhere, this last red dwarf will still be burning hydrogen, slowly, dimly, but still fusing, still shining. It will have no companions, no other stars nearby, just the cooling remnants of stars that died billions or trillions of years ago. And it will shine for trillions of years more. Patient alone, the last light in a darkening universe. Eventually, its fuel will run out. The hydrogen in the core will be exhausted. The fusion will stop. The star will cool, contract, become a white dwarf like all the others. And when it does, the stelliferous era will end. Officially, finally, the last star will have died. There will be no witness, no one to mark the moment, no one to say, that was it, the last star, the final light. Just the slow dimming of a red dwarf in an empty galaxy, noticed by no one, mourned by nothing. And the universe will continue, dark now, starless, but continuing. It is a lonely image, the last star shining alone, eventually dying unnoticed. But maybe it is also peaceful. The star doesn't know it is last, doesn't feel lonely. It just does what stars do, fuses hydrogen, emits light, exists, and when the fuel runs out, it stops. No drama, no existential crisis. Just the end of a process that ran its natural course. The last star will have shone for perhaps 100 trillion years. Longer than entire galaxies existed in the early universe. Longer than we can meaningfully comprehend. And when it finally dims, it will have done its job. Fused hydrogen into helium. Converted mass into energy. Shone light into darkness. That is what stars do. And this star will have done it longer than any other. The ultimate endurance, the final persistence. And then it will rest, join the white dwarfs and neutron stars and black holes in the long, slow cooling. Become part of the dark universe that will last for eternity, the last star, the final light. And in the silence that follows, the universe will remember, in its own non-conscious way, that once, for a brief time at the beginning, there were stars, and they were beautiful. After the stars die, what is left? Structures for a while, galaxies or what used to be galaxies, collections of dead stars, white dwarfs, neutron stars, black holes, still orbiting the galactic center, held together by gravity. But these structures aren't stable over the very long term. Gravitational interactions between the remnants cause some to be ejected from the galaxy. Others spiral inward toward the central supermassive black hole over timescales of 10 circumflex, 19 to 10 circumflex, 20 years. Galaxies evaporate. Most of their stars are ejected into intergalactic space. The rest fall into the central black hole, so even galaxies die. They don't explode or collapse. They just gradually dissipate, scattering their contents across the universe. And the ejected stellar remnants, white dwarfs, neutron stars, drift alone through the expanding void, cold, dark, isolated. They might occasionally collide with each other. Very occasionally, the universe is vast and mostly empty, but over trillions of years, some collisions will happen. White dwarf collisions might create type Ia supernovae, briefly illuminating the dark universe. But these will be rare, vanishingly rare, and eventually even the stellar remnants decay. If proton decay is real, and we don't know for certain that it is, then white dwarfs will slowly disintegrate over 10 circumflex, 40 years or so. The protons in the carbon and oxygen nuclei will decay into lighter particles, and the white dwarf will evaporate into a cloud of electrons, positrons, and photons. Neutron stars, too, would decay. The neutrons are less stable than protons once freed from nuclear binding. They decay, and the neutron star would dissolve. What remains are black holes, and they evaporate through Hawking radiation, but very slowly. Stellar mass black holes take about 10 circumflex, 67 years. Supermassive black holes take 10 circumflex, 100 years or more. But eventually, they all evaporate, all of them, every black hole in the universe, and when the last black hole evaporates, what is left? Photons. Low-energy photons, stretched by the expansion of the universe to wavelengths larger than galaxies. Plus a few stray electrons and positrons. Maybe some neutrinos, and that is it. That is the far future of the universe. No structure, no complexity, no stars or planets, or life or black holes. Just a dilute gas of particles at nearly absolute zero, spreading through infinite space. This is heat death, the final equilibrium state, maximum entropy. The universe has exhausted all its free energy, all its ability to do work, all its capacity for change. It is not the end of the universe. The universe will still exist, but it is the end of interesting things happening. No more stars forming, no more galaxies colliding, no more life evolving. Just sameness forever. It is the ultimate rest. After all the activity, all the creation and destruction, all the fusion and collapse and explosion, the universe settles into perfect eternal stillness, and there is a kind of peace in that. The universe, having done everything it could do, finally rests. All of this, the death of stars, the evaporation of black holes, the heat death of the universe, will take longer than you can imagine. Trillions of years. 10 circumflex 100 years. Timescales that make the current age of the universe look like a single breath. And there is something deeply calming about that. About knowing that the universe has time. That it is not rushing. That even after all the stars die, there is still forever left. The universe is patient. It has been expanding for 13.8 billion years. It will continue expanding for trillions upon trillions more. There is no hurry, no deadline, no pressure. And in the grand scheme, in the full timeline of the universe, everything that has happened so far is just the beginning, the brief, bright opening act. You are living in the first fraction of a percent of the universe's existence. The part where stars shine, where galaxies form, where life is possible. It won, lost. But it is happening now, and you are here to witness it. And when the stars die, when all of them have exhausted their fuel and faded, the universe will continue, darker, colder, but continuing. And in that darkness, there is peace. No more struggle, no more energy gradients driving change. Just equilibrium, stillness. It is not sad, not really. It is just the natural end of all processes. Everything runs down, everything reaches equilibrium, everything eventually rests. The stars will die, the galaxies will evaporate, the black holes will fade, and the universe will settle into perfect, calm stillness. And maybe, just maybe, that is what the universe has wanted all along. Not to burn bright forever, but to shine for a while and then rest. Like a person who works hard, lives fully, and then, when the work is done, sleeps. Deep sleep, dreamless sleep, peaceful sleep. The universe will have earned that rest. After 10 circumflex 100 years of existing, of creating and destroying, of forming stars and galaxies and black holes, it will have done everything it could do, and then it will rest. Forever, in the dark, in the cold, in the perfect stillness of heat death. And that is okay, that is allowed, that is natural. You, too, will rest. Not for 10 circumflex 100 years, just for tonight. But it is the same principle. After a day of activity, of thinking and doing and being, you rest. The universe does the same, just on a longer timescale. So rest now. Let yourself drift. Let the day's activity fade. Let your thoughts settle like sediment, drifting to the ocean floor. Let your breathing slow like a cooling white dwarf. You've been awake. You've been active, and now it is time to rest. The universe understands. The stars understand. Even they, burning for billions of years, eventually rest. And so can you. Sleep is not an ending. It is a pause, a rest, a letting go into darkness and peace. The stars will still be there when you wake, shining, patient, waiting. But for now, rest. There is a phrase that gets repeated often, sometimes almost like a cliché. We are stardust. But it is not a metaphor. It is literally true. Every atom in your body, with the exception of hydrogen, which formed in the Big Bang, was created inside a star. The carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, the calcium in your bones, the iron in your blood, all of it was forged in stellar cores through nuclear fusion, or in supernova explosions, or in neutron star collisions. Stars are element factories. They take hydrogen, the simplest, lightest element, and through fusion, they create heavier elements. Helium first, then carbon and oxygen, then neon, magnesium, silicon, sulfur, iron, and when stars die, especially when massive stars explode as supernovae, they scatter these elements into space. The gas enriched with heavy elements mixes with the interstellar medium, and eventually that gas collapses to form new stars and planets and life. The sun formed from a cloud of gas that was already enriched with heavy elements. The cloud contained atoms from stars that died billions of years before the sun existed. When the solar system formed, those atoms became part of planets. And when life evolved on Earth, those atoms became part of living things. The carbon atom in your hand might have been part of a star, S-core 10 billion years ago. It was forged through fusion when 3 helium nuclei collided and merged. It spent millions of years locked in the star, S-center. Then the star died, becoming a planetary nebula, and the carbon was expelled into space. It drifted. For billions of years, it drifted through the galaxy as part of a diffuse gas cloud. And then, about 4.6 billion years ago, it was swept up in the collapse that formed the solar system. It became part of Earth, and eventually, through countless chemical processes, it became part of you. That atom has traveled across the galaxy. It is billions of years old, and right now it is in your body, part of you, essential to your existence. Every atom has a story, and the story always includes stars, because stars are where atoms heavier than hydrogen come from. You are made of stellar remnants. Your body is a collection of atoms that were created in stars, scattered by stellar death, gathered into a planet, organized into life. You are, quite literally, the universe made conscious. Atoms that formed in stars, that drifted through space, that condensed into a planet, that organized into cells, that became a brain capable of thinking about stars. The universe creating complexity, creating structure, creating life, and through life, creating awareness. The stars didn't know they were creating you. But they were. Every breath you take contains oxygen made in stars. Every thought you think relies on carbon made in stars. You are stardust, thinking, breathing, alive, and someday your atoms will return to the universe. But for now, they rearranged into you, and that is remarkable. Let S follow a single atom, a calcium atom, one of the billions in your skeleton right now. Calcium is element 20. It has 20 protons in its nucleus. It is created through fusion in massive stars during the late stages of burning, oxygen fusion, specifically, or explosive nucleosynthesis during a supernova. Your calcium atom was created about 8 billion years ago, in a star perhaps 30 times the Sun's mass. The star had been fusing lighter elements for millions of years, building up layers, hydrogen, helium, carbon, neon, oxygen. And then, in the final days before the star exploded, oxygen fusion began. In the intense heat of the core, oxygen nuclei fused, creating silicon, sulfur, and calcium. Your calcium atom formed during this process, a collision of nuclei in a stellar core heated to billions of degrees. A moment of fusion that created something new. And then, seconds or minutes later, the star exploded. The core collapsed. The shock wave tore through the outer layers, and the calcium, along with everything else the star had created, was blasted into space. The calcium atom traveled outward at thousands of miles per second, part of an expanding shell of gas. Over thousands of years, that shell spread out, cooled, mixed with the surrounding interstellar medium, and then it drifted for billions of years. Literally, billions. Your calcium atom was part of a diffuse gas cloud floating through the galaxy, occasionally being disturbed by shock waves from other supernovae, but mostly just drifting. About 4.6 billion years ago, something changed. The gas cloud your calcium atom was part of began to collapse, maybe triggered by a nearby supernova, maybe just from its own gravity. The collapse formed the Sun and the solar system. Your calcium atom became part of the disk of material, orbiting the young Sun. And as that disk clumped together into planets, the calcium became part of Earth. For billions of years, it was just part of the rock, part of Earth's crust, locked in minerals, inert. And then, relatively recently, within the past few decades, that calcium atom was taken up by a plant, absorbed through roots, incorporated into the plant's structure, and you ate that plant, or you ate an animal that ate that plant. And the calcium entered your body, was absorbed in your digestive system, was transported to your bones, was incorporated into the mineral matrix that gives your skeleton strength. And there it is now, part of you, holding you up, giving you structure. An atom that formed 8 billion years ago in the core of an exploding star is now part of your skeleton. It has been on an incredible journey across billions of years, across billions of miles, through stars and gas clouds and planets and life. And it is not done. Someday you'll die, and that calcium will return to the Earth, will be recycled, will become part of something else. The atom will continue its journey, but for now, it is yours, part of you, essential to you. Stardust, holding you together. Now let's talk about iron, specifically the iron in your hemoglobin, the protein in red blood cells that carries oxygen through your body. Iron is element 26. It is the last element that stars can create through fusion. Fusing iron doesn't release energy. It consumes energy. So when a star's core fills with iron, fusion stops, and the star dies. Every iron atom in your blood was created in the core of a massive star in the final moments before it exploded as a supernova. Imagine a star perhaps 20 times the Sun's mass. In its last day of life, the core is filling with iron. Silicon fusion is still happening in a shell around the core, adding more iron every second. The star has maybe hours left. Your iron atom forms a nucleus with 26 protons and 30 neutrons, created in the intense heat and pressure of the core, one atom among countless others, and then the core collapses. In less than a second, it falls from Earth, sized to city, sized. The collapse releases energy. A shock wave forms, and the star explodes. Your iron atom is caught in the explosion, blasted outward at incredible speed, heated to billions of degrees by the shockwave. Part of the supernova's expanding debris. For thousands of years it travels. Part of a supernova remnant, a glowing shell of gas enriched with heavy element. And then the shell disperses, the gas mixes with the interstellar medium, and the iron drifts. Billions of years pass. The iron atom is part of the raw material of the galaxy, waiting. Eventually, it is incorporated into the solar nebula, becomes part of Earth, spends billions of years locked in rock in the planet's crust or mantle. And then, recently, it is brought to the surface, maybe through volcanic activity, maybe through geological cycling. It is weathered out of rock, dissolved in water, taken up by plants, eaten by animals, and eventually it enters your diet. Your body recognizes iron as essential. You need it to make hemoglobin. The iron is transported through your bloodstream to your bone marrow, where new red blood cells are being made, and it is incorporated into a hemoglobin molecule, placed at the center of a complex protein structure specifically designed to hold iron atoms. 4 iron atoms per H hemoglobin molecule, millions of hemoglobin molecules per red blood cell, trillions of red blood cells in your body. And that iron atom does something remarkable. It binds oxygen. When you breathe in, oxygen in your lungs attaches to the iron in your hemoglobin. The iron holds it. And then, as your blood circulates, the iron releases that oxygen to your cells. You are alive because of iron. Because iron atoms, created in a dying star billions of years ago, are now carrying oxygen through your body. Every breath depends on stardust. Every thought, every movement, every heartbeat, powered by oxygen carried by iron made in supernovae. You are not just made of stardust. You run on stardust. You've borrowed your atoms temporarily. They were here before you. They'll be here after you. When you die many years from now, hopefully. But eventually, your atoms will be released. Your body will decompose. The complex molecules will break down. The atoms will return to simpler forms. Carbon dioxide and water, mostly minerals, nutrients. And those atoms will re-enter the cycle. They'll be absorbed by plants, eaten by animals, washed into the ocean, buried in sediment, cycled through the Earth's systems. And eventually, billions of years from now, some of those atoms might leave Earth, maybe when the sun becomes a red giant and the Earth's atmosphere is stripped away, maybe through some other process. And then your atoms will be in space again, drifting. Free, they might become part of the sun's planetary nebula, scattered into the interstellar medium, mixed with gas and dust. And billions of years after that, they might become part of a new star, or a new life. The carbon that is currently in your DNA might someday be in a tree on a planet, orbiting a star that hasn't been born yet. The oxygen that is in your lungs might be in an ocean on some distant world. The iron in your blood might be in the core of a new Earth. Your atoms will continue. They're ancient, created in stars billions of years ago, and they'll persist for billions more, cycling through the universe, being part of different things, different processes, different lives. And that is strangely comforting. You're temporary, but your atoms aren't. They'll outlast you. They'll outlast Earth. They'll outlast the sun. They're part of the universe's permanent inventory, borrowed for a while to make you, and then returned to make something else. You're a pattern, a temporary arrangement of atoms. The atoms are ancient and will persist, but the pattern, the specific way they're organized to make you, is unique and temporary. And maybe that is okay. Maybe the pattern doesn't need to last forever. It just needs to exist for a while, to experience, to be. And then the pattern dissolves. The atoms are released, and the universe uses them to create new patterns. Life after death in the most literal sense. Not you continuing, but your atoms. Being part of new stars, new planets, new life, you'll return to the stars, not metaphorically, literally. Your atoms will scatter, drift, eventually become part of stars again. And in that sense, you're eternal. Not as a person, not as a consciousness, but as matter, as atoms, as part of the universe's ongoing creativity. You came from stars, you'll return to stars, and in between, you get to be human, to think, to feel, to wonder about stars. That is the gift, the temporary gift. And it is enough. On a clear night, away from city lights, you can see thousands of stars. Points of light scattered across the darkness. Some bright, some dim, some white, some yellow, some red. Every one of them is a sun. A massive ball of fusing hydrogen, converting mass into energy, shining across the light years. Some of those stars are like our sun, medium-sized, stable, middle-aged. They'll shine for billions of years more. Some are red giants, swollen and dying near the end of their lives. In a few million years, they'll shed their outer layers and become white dwarfs. Some are young, hot, blue stars, massive and bright, burning through their fuel rapidly. They'll die as supernovae within a few million years, and some of the stars you see are already dead. Their light left them hundreds or thousands of years ago when they were still shining. But by the time that light reaches your eyes, the star itself has died. You're seeing a ghost, a light echo of something that no longer exists. When you look at the stars, you're looking at different stages of stellar death. The whole process spread out across the sky. That bright star there might be a young star, just beginning its life. That dim one might be an old red dwarf, burning slowly, conserving fuel. That reddish one might be a red giant, shedding its outer layers even as you watch. You're witnessing stellar evolution, not in real time. Stars evolve too slowly for that. But across the population of stars, you're seeing every stage. Birth, life, death, all represented in the night sky. And you're part of it, part of the same process. Made of atoms created in stars, alive on a planet warmed by a star, conscious enough to look up and understand what you're seeing. The stars created you, and now you're looking back at them. The universe observing itself. Matter arranged into consciousness, contemplating the processes that created it. It is beautiful, strange, humbling. You're small, tiny. A brief pattern on a small planet orbiting an average star in an unremarkable galaxy. But you're also vast, made of the universe, made by the universe, connected to every star through the atoms in your body. The stars are dying, all of them, eventually. But before they die, they create, they forge elements. They seed the galaxy with the raw materials for planets and life. They die so that you can live, and when you die, your atoms will return to space, ready to become part of new stars, new planets, new life. The cycle continues. Always stars to life to stars to life. And for this brief moment, you're the life part, the conscious part, the part that can look up and understand. The stars are beautiful, dying, creating, giving, and so are you. Look up. Remember, you are stardust, and the stars are still shining. We've spent this time together exploring death, stellar death, the end of fusion, the cooling of white dwarfs, the evaporation of black holes, the heat death of the universe, all endings, all forms of stopping, fading, cooling, ceasing. And you might think that sounds sad, depressing even. All that beauty, all that complexity, eventually coming to an end. But maybe death isn't T-failure. Maybe rest isn't T-loss. Consider the sun. It will shine for 10 billion years total. That is its job. That is what it is meant to do. And when the fusion stops, when the fuel runs out, it won T because the sun failed. It will be because the sun succeeded. It did what it was supposed to do. It burned its fuel completely. It gave all it could give, and then it rests, cools, fades. Not because it is broken, but because it is done. Rest is not failure. Rest is completion. A star that burns for billions of years and then cools into a white dwarf has succeeded. It transformed hydrogen into helium, helium into carbon and oxygen. It shone light across the galaxy. It warmed planets, maybe enabled life, and when the fuel is gone, it stops. Not in defeat, but in completion. The work is done. You, too, are doing work. Every day, living, feeling, creating, experiencing. And at the end of the day, you stop, you rest, you sleep. Is that failure? Is sleep a sign that you couldn't keep going? Number sleep is necessary. Restorative, your body and mind need it. You rest not because you've failed to stay awake, but because you've done a day's worth of living, and now it is time to stop. The stars are the same. They shine for their allotted time and then they rest. Rest is built into the universe. It is not a bug. It is a feature. Everything that works eventually stops working. Everything that burns eventually cools. Everything that is active eventually becomes still. And that is okay. That is allowed. That is natural. The universe itself will eventually rest. After all the stars have died, after all the black holes have evaporated, after everything has cooled to near absolute zero, the universe will rest in perfect stillness, perfect equilibrium, perfect peace. And maybe that is what the universe has wanted all along. Not to burn bright forever, but to do its work, create stars, galaxies, planets, life, and then, when the work is done, to rest, like a long, satisfying day followed by a deep, dreamless sleep. The universe will have earned it. After 10 circumflex 100 years of creating and destroying and transforming, it will have done everything it could do, and then it will rest. Forever, and that will be okay. You are resting now, not forever, just for tonight, just for a few hours. But it is the same principle. You V worked, you V been active, you V been awake. And now it is time to stop, to rest, to let go into darkness and stillness and peace. Rest is not failure. Rest is what comes after success. We've talked a lot about darkness, the darkness of the ocean floor, the darkness of the deep universe, the darkness after all the stars die. And it is easy to think of darkness as emptiness, as absence, as void. But darkness is not empty. Right now, in the darkness of your room, there is air. Molecules of oxygen and nitrogen, moving, vibrating, present. There is sound, the gentle hum of electronics, the settling of the building, your own breathing. There is warmth. There is texture beneath you. There is sensation in your body. The darkness is full. It is just full of things that aren't light. The deep ocean is dark, but it is not empty. It is full of water, full of life, full of life, full of sound and pressure and movement. The darkness is rich with complexity. The dark universe, after all the stars have died, won't be empty either. It will be full of particles, photons stretched to enormous wavelengths, electrons, neutrinos, all the remnants of stars and galaxies, spread thin but present. And the darkness will be full of space itself, space-time expanding, carrying those particles farther and farther apart, but never reducing to nothing, always something, always there. Darkness is not emptiness. It is just the absence of light. But absence of light doesn't mean absence of existence. And in human terms, darkness is restful. Your eyes stop working so hard. Your visual cortex quiets down. The constant stream of visual information that dominates your waking hours, it stops. And other senses come forward. Touch. Hearing the internal sensations of your body, your heartbeat. Your breathing, the subtle shift of muscles relaxing. In darkness, you're more aware of yourself, of your body, of sensations that are always present but usually drowned out by sight. Darkness is not deprivation. It is a different kind of fullness, a fullness of internal experience rather than external stimulation. The stars will die, and the universe will be dark, but it won't be empty. It will be full of matter, full of space, full of the remnants of everything that came before. And you, right now, are in darkness or dimness, and it is not empty. It is full of you, full of your body's sensations, your thoughts, your breath, your presence. Darkness allows rest. It removes the demand for visual attention. It says, you don't need to see right now. You don't need to be alert. You can just be. The universe, in its final dark state, will just be. No more stars to form, no more galaxies to evolve. Just existence. Pure, simple, restful existence. And you can do the same. Right now, just be in the darkness, not seeing, not doing, not achieving, breathing, feeling your body in space, aware and present but not active. Darkness is not empty. It is full of peace, full of rest, full of the quiet presence of being without needing to do. Let the darkness hold you. It is not void. It is fullness of a different kind. Stars die slowly. We've talked about this. Red giants take hundreds of millions of years to transition from main sequence to white dwarf. White dwarfs cool over trillions of years. Black holes evaporate over 10 circumflex 100 years. Nothing in stellar death is rushed. Even supernovae, which seem sudden, violent, instantaneous, are actually the culmination of millions of years of evolution. The explosion itself lasts seconds, but the process that leads to it takes the entire lifetime of the star. The universe is patient with death. It doesn't rush. It lets things unfold at their natural pace. And there is something deeply calming about that, about knowing that endings don't have to be sudden, that transformation can happen slowly, gently, giving time for adjustment. You are falling asleep right now. And that is a kind of death, a small, temporary one, the death of waking consciousness, the letting go of active thought. And it is happening slowly. You are not unconscious yet. You are drifting, moving gradually from waking to sleeping, through stages of drowsiness and relaxation. Your brain waves are slowing. Your muscles are releasing tension. Your thoughts are becoming less focused, more dreamlike. It is a gentle transition, not sudden, not violent, just a slow drift from one state to another. Stars do the same. They don't suddenly switch from alive to dead. They transition, they go through stages. Red giant, planetary nebula, white dwarf, each stage blending into the next, and the transitions are so slow that from moment to moment, nothing seems to change. The star is just being, existing in whatever state it is in. You are doing the same right now, existing in the state between waking and sleeping, not fully either, just transitioning slowly, patiently. And there is no rush. You don't have to fall asleep immediately. You can take your time, drift, let it happen at its own pace. The universe has been dying, in the sense of moving toward heat death, toward maximum entropy. Since the moment it began, the Big Bang was the start of everything, including the slow process of running down. And it has been patient about it, taking billions of years to form stars, trillions more for those stars to die, trillions upon trillions for the universe to reach its final equilibrium state. There is no deadline, no pressure, just the slow, natural unfolding of physical processes. You can be patient with yourself, with your thoughts, with the process of falling asleep. Let it unfold. Let it happen. Don't force it. Don't rush it. Just allow it, the way the universe allows stars to cool at their own pace. Dying, whether it is the death of stars or the small death of sleep, is a patient process. Gentle, gradual, allowing. You are drifting. Now slowly, gently, and that is perfect. That is exactly how it should be. The universe is patient. The stars are patient. And you can be patient too. We've talked about cycles, how stars form from gas, live for a while, die, and return their material to space. How that material becomes part of new stars. How the process repeats. Everything returns. Nothing is lost, just transformed. The atoms in your body have been through countless cycles. They've been part of stars, part of gas clouds, part of planets, part of gas clouds. And after you, they'll be part of other things, other plants, other animals, other people, perhaps far in the future. Nothing ends permanently. Things transform, change form, but the substance remains, recycled, reused, returned. Water evaporates from the ocean, becomes clouds, falls as rain, flows in rivers, returns to the ocean, just cycling through different forms. Carbon is released by breathing, absorbed by plants, eaten by animals, released again. The carbon is the same, just moving through the carbon cycle. Atoms move through star cycles, planetary cycles, biological cycles, round and round. Never created, never destroyed, just cycling. And there is deep comfort in that, in knowing that nothing is wasted, that everything serves, even in death, that what seems like an ending is actually a transition to something new. When stars die, they don't vanish. They transform. White dwarfs cool. Supernova remnants expand. The material scatters, mixes, becomes part of new stars. When you sleep, you don't vanish either. You rest. Your consciousness dims, but your body continues. Breathing, repairing, processing, preparing for tomorrow. And when you wake, you return, refreshed, renewed. Not the same as yesterday. You've changed, learned, grown, but still, everything returns. Not always in the same form, not always recognizable. But the essence remains, the matter, the energy, the substance of things. The universe is a closed system, in a sense. Matter and energy can't leave. They can only transform, cycle, return, and you're part of that. Part of the endless cycling. Atoms that were stars are now you, and atoms that are now you will someday be stars again. You're a moment in the cycle, a beautiful temporary moment, and when your moment ends, the atoms continue. Return, become part of the next moment. Nothing is lost. Nothing ends forever. Everything transforms, cycles, and right now, you're returning to sleep, cycling from waking to sleeping, moving from activity to rest, transforming from alert consciousness to peaceful unconsciousness. It is natural, it is necessary, it is part of your daily cycle, and tomorrow you'll return again. Wake, be alert, be active, and then tomorrow night, cycle back to sleep, round and round. Daily cycles within life cycles within cosmic cycles. Everything returns, everything cycles, and in that cycling, there is continuity, connection, the reassurance that nothing is truly lost. You're returning now, to sleep, to rest, to darkness, and you'll return again to waking, to light, to activity. But for now, just let your cycle into rest. Everything returns. You will too. The stars are shining right now, even though you can't see them. It is night, or you're indoors, or it is cloudy. They're there, billions of them, scattered across the galaxy. Some are being born, collapsing from gas clouds, heating up, beginning fusion. New stars igniting for the first time. Some are in their prime. Like our sun, steadily fusing hydrogen, shining reliably, warming planets. Some are dying, red giants swelling, white dwarfs cooling, supernovae exploding, black holes evaporating, though so slowly you'd never notice. The full cycle of stellar life and death playing out across the universe. And the stars don't mind, they don't fear death, they don't cling to life. They just do what they do. Fuse, shine, cool, transform, following the laws of physics, participating in the cosmic cycles. They're peaceful about it, patient, accepting, and you can be too. You're dying, in the small sense, dying to today, letting go of waking consciousness, allowing sleep to take you, and it is okay. It is safe. It is natural. Tomorrow, you'll wake, you'll return. But tonight, let go. The stars are out there, shining, dying and being born and shining, and they'll still be there tomorrow, and the next day, and for billions of years after that. You don't have to watch them, don't have to think about them. They'll continue whether you're awake or asleep, and the universe will continue, expanding, cooling, evolving, cycling through its processes on timescales too long to imagine. It doesn't need you to stay awake, doesn't need you to witness it. It is okay to rest. The stars are patient. They've been shining for billions of years. They can shine without you for a few hours, and when you wake, they'll still be there, still shining, still dying and being born and cycling through their lives. But for now, rest. Let your thoughts drift like marine snow falling through dark water. Let your body cool like a white dwarf, slowly, gently, releasing the heat of the day. Let your breathing slow like the patient processes of the universe. Unhurried, natural, calm. The stars are dying, but they're also being born. The cycle continues, and you're part of it. Made of stardust, held by gravity, warmed by fusion. You're the universe, conscious of itself, ready to rest. So rest. Good night, stars. Keep shining. Good night, universe. Keep cycling. Good night, atoms. Keep existing. And good night to you. Sleep well. You are stardust, and the stars are with you, shining in the dark, patient and eternal, while you rest. Sleep now. The universe will be here when you wake. Sleep.